Okay, yeah. Welcome everyone to what I've realized is the 10th edition of the LAFI workshop. We started out in 2016 when we were so-called probabilistic programming semantics. So I'm really excited that we're now in our 10th edition. I think it's a very nice workshop where over the last 10 years we've really contributed some nice ideas to the community. There are fundamental ideas in probabilistic programming, semantics, like quasi-Borel spaces came out of this workshop. Lots of new inference algorithms, particularly in the area of inference algorithms, of differentiation algorithms, all kinds of applications. So it's really nice if you scroll through the list of
And the answer is that a lot of these effects stage away. So largely, we're generating PyTorch code, and so we can. Right now, we're fighting the PyTorch compiler, and it's often winning. But in a world where the PyTorch compiler was a little bit better, or where we moved some of this technology over to something like DAX, you would be able to stage away basically all of the effects
cable. Yeah. Yeah, I guess we can try it with the dongle.
Sure.
Yeah.
Because maybe you could on something that's not a Mac.
Yeah.
This might work better.
Right.
Yeah, you want to try plugging that in?
Yeah, let's try that first, and if
Yeah.
yeah, I can try this one. Because I think I'm the only one with
With a non-Mac.
a not Mac. Yes.
No.
Nope. So this is the output thing, but it's not.
But it's not doing anything. Okay. So what shall I do? So Maddie, take it away.
Hello? Okay. Is that good? Okay. All right. Hi, everyone. I'm I'm Matty Bowers, and today I'm going to be talking about some joint work with Alex Lev, Armando Soler, or sorry, Josh Tenenbaum, Vikash. Wow. Okay. Sorry, thrown off by the AV things, but some joint work with Alex Lev, Josh Tenenbaum, Armando Soler, and Vikash. So this is going to be a talk about the value of laziness in inference. And this is actually something that was realized very early in PPL literature, going back to the stochastic Lisp of Daphne Koller and colleagues in 1997. But it's something that's been largely abandoned in the past decade or so as we've developed very modern, sophisticated inference techniques. And so first, let me tell you a bit about why laziness has been long recognized as useful for inference. So say we have a probabilistic program like perturb that we've written, called perturb, that takes a string and it's going to introduce some typos into that string by randomly inserting and deleting characters. So if we run perturb a few times on our input, like the word lazy, we're going to get a range of different corrupted strings. And just to break down the code for this program a bit, it's going to start with a helper function that takes a string and inserts any number of characters. It also has this function maybe keep that's going to decide whether to drop a character. And finally, the actual implementation of perturb is going to, if the string is nil, just insert any number of characters. And if the string is a cons, it'll decide whether to keep that first character, insert any number of characters after it, and then recurse. So in essence, this is walking along the string, deciding whether to drop characters, and also at each point inserting any number of characters. And a natural question about a program like this is, say, what is the probability that we corrupt our input string to some particular output, like the string lucky? So one approach to this is going to be to enumerate all the possible executions of the program. Right? So for example, at the first step, we could decide to keep that first letter and insert a U and a C after and get this prefix luck. And here I'm showing the completed prefix in this bold green, and then the recursive call in red. The remaining recursive call, which might add additional characters. Now, another option is we could drop that first L and say insert the whole word luck. Or we could say drop the first L and insert literally any prefix. So for example, DEN. And if we continue this process and unroll this recursion, we end up at the bottom with this tree, or at the bottom of this big tree of execution paths, we end up with all these concrete corrupted strings. And if we add up the probabilities of the paths that lead to our target string, lucky, then we've solved our problem. But the problem with this is a really big tree. In fact, it's infinite, and it's even infinite at the very first level, because we can insert a string of any length through this recursive maybe insert function. So standard enumeration is never going to terminate. But what if we adopt the lazy semantics for the program? So when we want to evaluate the lazy expression equals of perturb lazy to lucky, we're going to thunk perturb lazy, right? We thunk our arguments. And then the implementation of equality is going to have its usual implementation that is going to run perturb just enough to figure out the possibilities for that very first character. And importantly, it's only going to actually recurse on the rest of the string if that first character matches. And this ends up making a huge difference in this case. So it brings us from this infinite tree to actually a finite tree, where essentially we no longer explore any of the paths that involve a prefix that doesn't match, that isn't a prefix of our actual output. And another way of thinking about what's happening here is that we're essentially laziness by not evaluating choices that are in thunks that don't get forced. It's implicitly marginalizing over all of those choices in the unforced thunks. Now, that said, there's still an exponentially large tree here. And it's exponential because there's a lot of work that's being redone at each step. Or rather, there are many paths that lead to the same intermediate state. And modern techniques for inference are going to exploit independent structure in the program to avoid this, avoid redoing work here, and essentially bring us from exponential time in the length of the string to polynomial. So this talk is going to be about how to combine modern inference techniques that do that kind of, that use independence in that way with laziness. So in particular, we're going to focus on a technique called knowledge compilation. Knowledge compilation is a state-of-the-art technique for inference in discrete probabilistic programs. And at a high level, what it does is it compositionally translates some input probabilistic program to a representation of all of the paths through that program. And importantly, this representation is a graph instead of a tree, so it can capture how multiple of these paths actually lead to the same intermediate state. So this allows it to capture exactly that sort of sharing that we wanted in the perturb example. But the issue here is that standard knowledge compilation is strict. So for example, when compiling an expression like x equals E1 and E2, we're first going to compile E1, then compile E2, and then we're going to use these two to construct our result. And E1 ends up getting compiled whether or not it actually used an E2, which ends up on programs like perturb, meaning that we fail to terminate for the same reasons as strict enumeration. So how do we make knowledge compilation lazy? Now, in this talk, I can't give a full overview of our algorithm, but I wanted to point out a couple of the key ideas of it. So one component of our approach is that we're going to delay the computation of sub-expressions until they're actually forced, much like in normal lazy evaluation. So for example, with let x equals E1 and E2, we're simply going to thunk E1, and then we'll go ahead and evaluate E2 only forcing E1 in the case where E2 actually uses it. And we're similarly going to use thunks for compiling function calls and constructor applications for data types like lists or trees. So this ability to partially compile expressions of list types turns out to be useful, but it's actually not enough alone to get the full benefit of laziness. So to see why this is, let's look at a simpler example than perturb. If, for example, we have this program that in its first step generates a random list of Booleans with random length, and then in the second step, evaluates whether all of these Booleans are true. Now, note that so far, if we're doing a lazy evaluator, if we tried to, at this point, just evaluate B, there are going to be infinitely many ways to get there, because there are infinitely many random lists of Booleans that we can create. But if instead we had an expression like this, where the last line of the program only evaluates B if the length of x is, say, less than 4, then the lazy semantics is going to have a finite set of execution paths that lead to these short lists. But how can we actually capture this in the knowledge compilation? Because if we just thunk x's and thunk b, and then evaluate our thunks when we get to this b call in the branch, then, and we just do classic knowledge compilation, we're going to end up compiling that whole big infinite representation for all of the paths, including the ones involving longer lists. So the key here is we can use this path condition that length x's is less than 4. So by the time we actually force this thunk in a branch, we don't need to compile our representation of the whole distribution of V. We can just compile the part that is consistent with the current path condition. So this generally is a key benefit of this lazy compilation approach. We get to compile the conditional distribution of a thunk given its path condition, which can often be dramatically smaller than the full distribution of the thunk. In this case, bringing it from infinite to finite. Yeah. And this can make knowledge compilation much faster, even on examples where standard knowledge compilation does terminate. So, for example, there are lots of programs with this kind of high-level structure, where we have x's coming from some distribution, and then we're asserting that x's, we're observing that x's is equal to some concrete list of values. And because each element of x's is only forced if all of the previous elements equal their observations, we can actually just represent these conditional distributions of the next element given all the previous ones were the observed values. So for example, on the distribution of the third element, we can basically evaluate the conditional distribution that the third element is 6, given that we already know that the first two are 1 and 3. Now, that was just a high-level view of some of the benefits of lazy knowledge compilation, and there's a lot more that we're happy to chat about at the poster. But let's talk about what this buys us empirically. So we've implemented this approach in Julia and compared it to both enumerative approaches and standard knowledge compilation on a range of benchmarks. So first off, on the DICE benchmarks, a lot of these, these Bayes nets and network reachability problems don't really exercise the kind of data structures where laziness really pays off. So generally, we either do better on some or worse on some, depending on overheads of the laziness. But then additionally, we evaluate on these more structured distributions. So in particular, we have a hidden Markov model, a PCFG distribution, that perturb example, a more complex version of it, and sorted list generation, sorted list generation problem. And with all of these, we end up running in a matter of milliseconds instead of seconds or minutes, because we can just represent those conditional distributions. Right. Oh, and I should mention, right, HMM is actually, I suppose, a special case because that's one where there's DICE can still run fast because of the independent structure in the HMM, but for all of the other examples, there's a dramatic effect from using laziness. Now, if we vary the output sizes on these examples, we see that laziness allows for polynomial scaling, while DICE scales exponentially. And additionally, for all of these examples, we've been giving DICE a recursion bound, and we've been setting it just low enough that DICE produces the right answer. But if that bound is set too low, you get a wrong answer. And if it's set too high, runtime scales exponentially, even for a fixed output size. So that's another place where laziness pays off and effectively kind of infers the right bound for your recursion. And finally, there are two other evaluations we did, which I'm happy to chat about at the poster later. One on randomly sampled programs from a range of grammars, and one where we put our program in the loop of MCMC-based probabilistic program synthesis. And so in summary, we've revisited this classic idea that laziness implicitly marginalizes over irrelevant choices. We've adapted a modern knowledge compilation method to benefit from it. And there's lots we didn't cover, so please come by the poster if you're interested in chatting about things like how we actually do knowledge compilation here, how we handle cache validity with laziness. There's fuzzing and synthesis evaluations, a programmable approximate inference version of our algorithm, actual formalization of this in terms of the lazy PPL semantics of dash et al., or anything else that you're wondering about. Thank you.
Thanks very much, Maddie. I think we have a moment for questions while Jack comes to set up.
Hi, thanks for the talk. I think I missed one detail is in one of your examples, you have an observation and you say if the observation doesn't match, you cannot evaluate the rest. But how do you compute the normalizing constant if you don't evaluate all the branches?
Let's see, how do you compute the normalized? So if the, let's see, I think we don't, well, right, we're summing over actually all of the paths, so we don't need to compute a normalizing constant for the, yeah, well, we can also just chat offline at the poster if that's good. Sorry.
Jack, can you get the microphone?
Sorry. Thanks. All right.
I'm very happy that we have a poster session later. There's lots of things to discuss with all of these talks, and we're really rushing through them now. But at least we'll have time for coffee as well. So, Anthony, take it away.
All right. Thank you. Hello, everyone. I'm Anthony. I'm a graduate student at the University of Illinois. And this is a project on semantics for probabilistic programming languages. A little bit about me. I do math. That started out as topology and logic, but now through an internship at Sandia, that's really moved toward PL theory. So this is joint work with John Itouch. Shout out to him. And what we're working in, with the field we're working in, is trying to come up with an abstract machine semantics for inference. Why are we doing this? Well, we're really aiming for higher order contextual equivalences in probabilistic programming. This is actually something that's going to be rather difficult to do because probabilistic programming shares a lot of similarities with another programming language idea, fresh name generation. And already in fresh name generation, we get these higher order equations, which are things we want to verify, but are things that are rather difficult to verify. So this sort of Rosetta Stone to go from probability to fresh name generation is this grabbing a fresh name that is literally sampling a random variable. And then what I've written down below is this one example of a higher order equation called the privacy equation for fresh names. One that famously is proven for some models of fresh name generation in Ian Stark's thesis on it, but not all. So if we take a step back now, we have these denotational models for probability through, say, quasi-Borel spaces. These are fully abstract, precisely because they do not prove the privacy equation. So what can we do instead? A lot of the denotational models, the way they work is using some sort of monad, like a name generation monad, to describe how to obtain a fresh sample. However, we don't actually need to use this process of how to describe a fresh sample when we're reasoning about a fresh sample once we have it. And so we're going to kind of split the problem into two pieces. Obtaining the fresh sample and then using the fresh sample. And this makes use of a pretty recent tool called atomic sheaf logic. Came out of a paper by Alex Simpson last year. And the kicker here is that while there are many possible approaches to obtaining a fresh sample, all those approaches, in a sense you can make precise, are this thing called atomic equivalence. So if we can somehow figure out a way to build in atomic equivalence, then whatever that framework is a way to talk about fresh samples without getting into the details about that process of how to obtain that fresh sample. In some sense, since we can kind of recognize what a fresh sample looks like, if we can pick a sort of non-deterministic rule for, okay, if you just give me a fresh sample, any fresh sample, and I know how to use it, then atomic equivalence is going to sort of make that non-deterministic idea deterministic. All right. So I talked about how we're going to split the problem into two pieces, this notion of contextual equivalence in probabilistic programming. The first piece are these contextual equivalences, these equations coming from the usual semantics of a programming language. So we can think group one being, maybe this is where an abstract machine lies. Maybe this is where some sort of denotation lies, but this is the familiar equations we might expect from a programming language. Whereas group two is this new phenomenon in the context of whenever we have sampling. So in the case of probability, we have a notion of entropy, and our random variables now are going to take seeds in the entropy and push out values. So they're of course functions from a source of entropy. On the other hand, there's another paradigm here taking advantage of that fresh name generation analogy, that source of entropy kind of behaves like a source of fresh names. And so there's this idea here where symmetries in that source of entropy kind of behave like alpha equivalents of names. And that's those kind of alpha equivalence type equations, I'm going to call those group 2. So here are 2 examples of that. I sort of just described it. The first one is that alpha equivalence as we perhaps normally expect it in the context of names. The second one appears in the probabilistic setting already from a while ago, where here symmetries of the source of entropy are, literally speaking, symmetries of some probability space. We see this already where our contextual equivalences now for probabilistic programs are preserved by these sort of measure theoretic symmetries. So we're going to try to tackle the group 2 equations. We're going to find a way to push them to the side so that our programming language is respecting them, but so that we don't have to think about them in front of mind at all times. So the way we do this is through some sort of crypty-world model. And the idea here is, instead of working in a typical universe of sets, we're going to build a bespoke universe of sets. And in that bespoke universe, we'll have this atomic equivalence to play with that will handle those symmetries. So the idea here is, given such a notion of crypty-world, which I'll describe in a few moments, we can talk about this abstract machine. And this abstract machine, if we reinterpret it now, instead of the usual set theoretic abstract machine in this sort of new crypty-world-like or some sort of modal logic perspective, then that abstract machine is going to have a unique notion of sampling. So to really point out where this crypty worlds are coming to use, there are those group 2 equations. Those are those equality up to renaming type ideas. Those are going to be handled, literally speaking, through those worlds. All right. So I talked about how there's going to be this bespoke universe of sets to accomplish this, in order to bring in atomic equivalence. What do I really mean by that? Well, we have our crypty worlds as our source of entropy, these probability spaces, and by working in that sort of atomic sheaf logic, what it allows us to do is, instead of just having our judgments, our usual judgments, some sort of statement phi about the semantics of a program, we can always guard these judgments now with what is the source of entropy in which that judgment is happening. So this is called the forcing semantics. And we can think of it as, instead of talking about whether or not a statement is just merely true or false, it's now pertinent to say it is true when the source of entropy is this probability space omega, leaving open the possibility, of course, of it being not true for other spaces. All right. So the idea here is, once we have this extra judgment, we can use set theory in sort of the usual way. This is what Alex Simpson really refines in the atomic sheaf logic. But we treat our we sort of replace anything that looks like a set with now this atomic sheaf, and now we can talk about an abstract machine in much the same way we would in the traditional way. We have instead of a set M, we have a sheaf M of states of some system, and we have some relation just saying when does one state rewrite to the next state. And instead of talking about this as a subset, we'll talk about it as a subsheaf. And so the sort of statements that we would, sort of soundness statement we would expect from such a system, instead of saying that this is an abstract rewriting system that is strongly normalizing, we could now guard it with the source of entropy, omega. All right. So why do this? Well, atomic sheaves, unlike sets, have atomic equivalence. So if we write our abstract machine in this framework, now all of a sudden We can talk about atomic equivalents of states. We can talk about atomic equivalents of sampled variables. And that will be our surrogate for equality now. This is our equality up to renaming, but moved to probability. So just a little more on the details of that. We need a notion of name. This is our random variables. This is what we're sampling. And the point here that one can show is that this construction that takes in our probability space and outputs now a set of random variables is an atomic sheaf. So it fits into the framework. And if we use the atomic sheaf language, then this in fact does become two random variables are atomic equivalent if and only if you can find a permutation of the symmetry of the source of entropy that sends one variable to the next. Once we do that, the machine looks a lot like a stack-based machine. For example, we have a SECD type machine model for doing probabilistic sampling. And in many ways, it behaves just like before, but now we have this extra Kripke world clause guarded to it. But then we just add in a new rule for sampling. And the point here is that now that we have atomic equivalence, this rule is sort of the non-deterministic one made deterministic. What we do is we end up trying to find a way to just tackle in any possible random variable to sample. And since such a random variable is unique up to atomic equivalence, this is now a deterministic transition system. So I just want to leave with 2 points then. First, up to atomic equivalence, there's one way to obtain a fresh sample. And so then if we move our paradigm now from set theoretic to atomic sheaf logic, then our abstract machines can talk about how to use these samples, but without having to specify, say, a name generation monad or any type of mechanism for getting that sample. Instead, atomic equivalence will just give us that for free. All right. Thank you, everyone.
Thank you, Anthony. We have about 2 minutes for questions. Our next talk is remote, so if AVD can start setting that up.
Hi, thanks for the talk. At the beginning of the talk, you said that existing models of probabilistic programming were not fully abstract because they didn't validate the privacy law.
Yeah.
But I thought that quasi-Borel spaces do validate the privacy law. Like, is that, am I misremembering the work of like Dario Stein on probabilistic programming semantics for name generation?
So there are multiple privacy equations. And that quasi-Borel spaces paper, they prove some privacy equations, but they don't prove all. So it's still there's still a gap from like the denotational model to say a fully abstract one. Yeah.
Thanks very much. Do we have our remote presenter ready? Yeah?
the automaton, instead of popping a query, performs a push. And in this way, we model rejection sampling. So when we have to reject a trace, we pop all stack symbol up to the query, the topmost query on the stack. And but precedence relation guarantee us that we don't go beyond the query we are in while popping. And so once you have built the whole automaton, the inference problem of the original program corresponds to solving a system of polynomial equations on the automaton, and intuitively they are tuples pxr, where pxr is the probability that state p returns from function x with return value r. And this system of equations are well known and studied in model checking. They're known as termination probabilities. Bad news is that solutions to this, the solutions of these systems are in general irrational and not even expressible by radicals. So our approach is use an iterative method called optimistic value iteration, OVI. And with this method, we compute lower and upper bounds to these values. So our solution, in a sense, they are exact because they are not sampling based. So we are guaranteed that the actual solution is between the lower and the upper bounds we compute. And also, these bounds can be made as close as one wants to the actual values. And we also have a couple of experiments already on with this method. One is the very famous Schelling coordination game, and we generate some equations, and we can solve them very fast. And we tried to use WebPPL for this problem, but it cannot help. And yeah, to conclude, I'm happy to chat about and also in the poster session about the notational semantics for this class of programs. We couldn't find many, and also more experimental models and applications for this nested programs. Thank you.
Thank you, Francesco. Do we have any questions
Okay.
here in the room?
Thank you for the talk. Just one quick question, but do you need to assume that your program almost surely terminates for nested inference?
No, we don't need to assume that. We can compute sub-distribution if the program has some probability of divergence, or yeah, we don't need to assume that.
Okay, if there are no more questions, then I'd like to propose that we take a coffee break. And yeah, for all this
Hello? Oh, there we go. Thanks. Oh, yeah.
Sorry, are you using black cable?
Yeah, the HDMI.
All right. Okay.
Oh, that might, I hope it's not my fault.
Usually it starts by saying something about HDMI, which hasn't happened so far. So
I don't see another monitor.
Linux, right?
Yeah.
Okay. What about trying one of these dongles? Are you open to the idea?
Yeah, I can give it a go, but
This was working for me earlier with the Linux machine.
well, let me just try one more time.
This thing was working with Linux
Oh.
for me. Yeah.
Okay, I'll give it a go.
You can just maybe try this.
I'm not confident this is going to work well.
Okay.
Yeah. I don't know if my computer's going to recognize this.
I actually have the same computer.
Oh, really?
Yeah, at home. So
Is it as badly configured as mine, though?
all right.
We should put some elevator music or whatever the genre is called. Like, yeah, bear with us.
Let's switch back to HDMI and see
Okay,
if that
all right,
helps.
yeah, yeah. All right, yeah.
Give it that.
To use Ronder or whatever.
Hmm? Yeah,
Yeah.
that worked.
okay.
That's what I did last time. So.
Okay, does it look like it's recognizing like the resolution? Can you see the resolution for this thing?
Oh, yeah,
Oh,
yeah,
okay.
there we go. Yay.
All right, cool.
Cool.
Okay, so yeah, let's get started.
All right. Okay, so in the interest of time, I want to talk about this data structure called open hypergraphs. And they're basically a data structure for representing syntax. And you'd use it where you'd use a tree, except where your terms are more kind of circuit-like. So I've got this picture, this F and G thing on the top here, and that, you can kind of think of that as the term x squared, right? So it has this operation F, which is going to copy its input, and the white operation is going to multiply its two inputs together, and so it takes some x and gives you x squared. And the difference with trees, obviously, is like your operations can have multiple outputs. So sort of this multiple input, multiple output thing very naturally. And there's some data parallel algorithms for constructing these things algebraically, so by tensor and composition in a category, but also differentiating. So that's what's pictured in the big complicated diagram on the bottom. That's what I mean by a derivative of that diagram. But the sort of the headline is really that this transformation from the top to the bottom is kind of like an ahead of time autodiff algorithm, and you get a symbolic term out of it. And this is kind of talked about in this paper, data parallel algorithms for string diagrams, but there's some other stuff floating around as well. So I'm not going to talk about category theory too much, but the one thing I do want to say is that when I say a term, what I mean is a morphism in the strict symmetric monoidal category freely generated by some signature. But in sort of normal human language, what that means is you have some set of objects, and think of these as like types. So for example, you might have a type of integers, and some set of operations. So here we have like copy and multiply, and you just sort of plot these operations down on the page, and you wire them up however you like. But when you do this, it is actually the case that these things form a category. This data structure is like kind of directly from the math, so to speak. Now this data structure, sort of abstractly, open hypergraphs, cospans of hypergraphs, have been known about for a while. It's kind of folkloric. I know it from this really nice series of papers, String Diagram Rewrite Theory. But this talk is really about a very specific representation of these hypergraphs, which like works well for GPUs. So it's all very data parallel. And so I'm going to tell you about the data structure, talk about these algorithms for constructing it, and then finally how to take derivatives of these things. So going back to our x squared term, that's this string diagram here. My mouse showing up? Good. This thing below is kind of a depiction of the data structure. And there's a few different things going on. So you have these blue boxes, and these are representing the sort of dangling wires here. You have these black nodes inside this gray box, and these are the hypernodes of the hypergraph. The white boxes are hyperedges, and the nodes correspond to wires of your diagram. So this 0 node here is the input wire. This 1 node here is this top wire here. And the hyperedges correspond to your operations. And so just down here are the sort of concrete numbers in this particular representation. So each hyperedge has a list of sources, so the source nodes sort of feeding into it, and the target nodes to which it writes. And it also has a label saying what operation it is. And so the sort of naive approach to represent this is you have, for each hyperedge, you have a tuple of its sources, its targets, and its label. Oh, I should mention these are ordered lists. It's really important they're ordered because obviously if you, in a general operation, if you swap the order, then it might do something different. And this is kind of an array of structs representation, which is not super nice for GPUs. So the obvious thing to do is use a struct of arrays. And that's exactly what this is. So the actual concrete data structure is just these 8 arrays here. The bottom 2 are segmented arrays. I'll talk about that in a sec. But we have an array of labels, W. So all the wires in our diagram they're labeled with the object in the category or like the type. So in this case, we only have ints. The operation, each operation also has a label, so copy and multiply. Then we have a list of nodes that are inputs. So we have 0 as the input node, 3 as the output node. And then lastly, we have this thing of sources and targets. And these are just concatenations of the previous sources and target arrays we already saw. So when I said a segmented array, what I mean is really a pair of arrays where the bottom is a concatenation of some arrays and the top is just a list of sizes, basically. So that's the representation. Now we need 2 operations on it for it to form a category. We need tensor and composition. Tensor is just stacking, right? So if we stack copy over multiply, we get something like this, which copies its first input and multiplies its second 2 inputs. And then composition is you feed the outputs of one thing into the inputs of the other. And to just quickly sketch the way this works and why it's data parallel, that's kind of the thing I'm trying to convey here. This tensor is just array concatenation with some renumbering. And the renumbering is very easy, you just add an offset. So if you look at the sort of input arrays here, there's 2 of them, you just sort of squish them together. But of course, we've renumbered the wires in the right-hand side of this. And basically, all the label arrays you just concatenate. Any of the arrays involving indices to wires, you have to do this renumbering, but it's very easy. It's completely data parallel. In fact, you should be able to do it in constant time if you have enough processors. Then composition, you first do a tensoring. So that's what I've pictured on the top here. And then you do an identification of wires. So this is basically saying you put all the diagrams into one big diagram, and then you identify the bits that got glued together on the boundaries. And then, of course, you also need to delete the parts of the interfaces that shouldn't really be exposed anymore. So here we're gluing the outputs of F into the inputs of G, so we identify 1 with 3, 2 with 4. And the way you do this identification is by connected components, and that's pretty fast on a sequential machine. It's linear time, but it's also very fast on a parallel machine. It runs in logarithmic time, so it speeds up. It's data parallel. And in general, there's actually an algorithm to construct one of these things from a general tree. So if you have a tree like F compose G, tensor H, the nodes are compose or tensor. And the obvious thing to do is this just sort of inductive thing where you use your tensor and compose algorithms. This is very slow because you're doing n linear operations, so that's not good. But instead, the trick is you tensor all the leaves together, and then you use connected components to wire it all up at the end. It runs nice and fast. But the point about doing this wiring all at the end is that, this is a trick we use pretty much everywhere in the code, including for the autodiff stuff. Before I talk about autodiff, I have to tell you about this condition monogamous acyclicity. So earlier I said you plop your operations down on the page and you wire them up however you like. That doesn't actually work. That doesn't get you a morphism in the category, so I lied. It gets you a morphism in a different category with some extra structure. I'll show that in a minute. But if you want a genuine morphism in the category generated by your signature, you need this monogamous acyclicity condition. I'm not going to tell you what it is, but it's fairly simple. It forbids things like I've pictured here. And of course, it's preserved by tensor and composition. So if you build something inductively, then it's still sort of within the category. Now, if you don't have this condition, the extra structure you get is this special Frobenius structure. So it's these 4 operations plus some equations which are not pictured. But now I can show you the term corresponding to that weird open hypergraph I showed you. And you can see that you can do sort of feedback, you can bend wires backwards, you can split wires, you can join wires. And part of this structure is going to be very useful for doing the autodiff. So in particular, being able to bend wires backwards is going to let us have information flowing from left to right in the kind of forward pass of your neural network and right to left in the sort of gradient reverse pass. So to be clear about what I mean by taking a derivative, I mean computing a reverse derivative of a morphism. So this is defined in this paper, reverse derivative categories. It's a very nice paper. I did a kind of inductive version of this with string diagrams, but the sort of TLDR for the purpose of this talk is for every operation in your category, if you have some f a to b, you also need a reverse derivative, which goes from the input a, the output gradient b, and it will give you an input gradient a. And they're composed by the chain rule. The problem is the chain rule has both f and r of f in it. So the way this is compositional is actually as a pair of f and r of f. And this is actually a lens, but I'm not going to talk too much about that. And it seems like if we want to compose things in this way, we're going to have to take our diagram, break it down into its constituent primitive operations, and then inductively build it back up. But as we already know, this is like n squared. This is not fast. So what we want is something which is linear time or logarithmic, if we can get logarithmic in parallel. And we don't want to use this inductive approach. So we can use optic composition. And the sort of intuition for this is, like I mentioned earlier, your sort of data flows from left to right, and your gradients flow from right to left. So an optic has sort of 3 things: a forward map, a reverse map, and this residual communication between them, M. And in terms of PyTorch, actually it lines up very, very nicely with PyTorch, where you might write a forward map. So this is for multiply, taking x1, x2, multiply them together. That's the output. And you also have this residual communication where you save x1 and x2 for the reverse pass. Now your backward map takes that context. So this would be x1 and x2 on these wires. And it will multiply your gradient output coming in here by x2 and also by x1 on the second output wire. So what does that actually look like as a diagram? Now we use the special Frobenius structure to construct this thing. So you can sort of see that what's down here is actually an input, and it sort of loops around here, feeds back into the backwards map, G backwards. And similarly, this down here on the bottom left is an output. So the thing to note here is this is actually not monogamously cyclic because we use this Frobenius structure. And so it's not a term in our original category. We can fix that though. And the way that we fix that is by adding this extra, we can just bend those wires around basically. So here's a kind of picture of differentiating our x squared term. And you map your f to its forward and reverse components. You map your g to its forward and reverse components. You obviously have to connect the residuals up. These things now compose together, as in this diagram. So you just sort of plug them together like that. And then you have to bend around the wires at the bottom so that this here is actually an output, and this here is actually an input. And I guess if I want to try and convince you informally, if you take those bottom 2 wires and you pull them, all the Frobenius structure will disappear. It's like when you see someone tie a knot and they pull it and the knot disappears. It's a bit like that. So just to try and convince you that this is that computing this diagram is actually data parallel. The sort of basic thing is for each operation fi in your input term, you compute its forward map and you sort of stack these up. That's basically just a map over an array. You do the same with your reverse maps. You have to do a bit of funky wiring here. But that's basically it. And now you have something sort of the right shape. There's a bit of extra bookkeeping involved, but that's basically the idea. So what can you actually build with that? Obviously, the example I gave you is very, very simple. But if you take as your sort of generating operations tensor shapes, and you're generating objects, tensor shapes, and you're generating operations, things like, matrix multiplication, things like this. Then you have a differentiable array language, and we have essentially just enough here to train like a simple GPT model, so nano GPT in this case. There's some other stuff I'm not going to talk about to leave time for questions, but ask me if you like. Yeah, and that's basically it. We're sort of working on this at my company, Hellas. We're hiring, so shameless plug at the end. But yeah.
Thank you, Paul. So, any questions in the audience?
Right, thank you. So you're saying the differentiation on the circuits is something that can happen in a data parallel manner, and the construction of the circuit out of the syntax can be done in a data parallel manner. So for what sort of applications do you think that is important? Because I always imagined this being a compile time thing.
Yeah.
Or do you imagine doing this sort of transformation at runtime and on a GPU?
So one thing I wanted to do, which I've not got around to, is if you're doing program search and you have very large terms and you want to do a lot of these things, then it becomes sort of in the loop, and so you need to be able to differentiate these things. And specifically, what I'm thinking about here are circuits. So trying to find good circuit models where you're using some notion of differentiation. And also, I should mention, like, because this is optic composition, really, it's not really an autodiff algorithm. It's an optic composition algorithm. It generalizes to other things as well that are sort of optic shaped, like, I hope, incremental computation and some other things. Yeah.
Great, thank you.
Are there any other questions? If not, I have a very high level, maybe silly question. So what was the reason to start working on this? Was it motivated by a specific application in mind, or?
It was partly the desire to do differentiation of string diagrams, and specifically with an eye to doing this circuit thing, but also kind of a general ideological attempt to do everything with string diagrams.
All right. Okay.
So, yeah.
All right. Okay. Oh wow, that calls 2 extra questions. Let's take them.
Hi, thanks for the talk. I was wondering, can you use this to prove optimizations on circuits, like rewrite rules to simplify the circuits?
Sorry, what you mean? What's the goal you're trying to prove exactly?
Like you can compile whatever you want into a circuit, and can you, I don't know, like came up with some rewrite rules to simplify the circuits, like to do some kind of optimization?
Oh, I mean, rewriting is not something I've looked at, but like the theory of rewriting these things is like fairly well known. There's some software to do it. I think Chip by Alex Kissinger. But
right. But you're not. Are you doing that with your?
We're not doing rewriting, but it's like possible in principle. Yes.
Hi, thank you for this talk. I have a question on the functions you can differentiate, because it seems that there is a correspondence here between the string diagram and the function. And for a Frobenius structure, I could see a polynomial, but if I want a more complicated function, does it make sense to describe it as a string diagram? What would that look like?
I mean, the most complicated function that I've applied this to is GPT-2. So. But in terms of like features, like for example, higher order functions are not something that I handle right now. I don't know how you do that in principle, but there's better people in this room to ask, which I plan to. And things like loops, you'd have to unroll your loop first. But I think there's probably a nice categorical way to describe this. Does that answer your question?
It does answer part of it. I'm curious on the, I'll ask you later too, but I'm curious on like what the categorical structure looks like that.
Okay. I mean, I have ideas, but yeah.
I think this is the end of this talk. So our next talk is going to be a remote talk again. Thank you, Paul, again. Yeah, thank you very much. So the next talk is by Owen Lynch, and it's on data-oriented design for differentiable probabilistic programming. Let's get it up here. I learned that the speaker is already there, but so it's just a matter of bringing them on the screen.
Hello?
Hi. Hi, Owen.
Hi.
So, hi,
Okay,
can you
great.
hear me?
Yes.
Great, we can hear
Yeah.
you like loud and clear. So we are waiting for the video to show up. We have that now.
Okay.
Yes, and maybe like
Is already there,
sharing
but
slides, I think. Assuming
Yeah,
you have
do you-
slides. All right.
Yeah. Great. Can you hear me and see me and
Yes.
hello?
Yes.
Hello?
Yeah, everything's working great. Yeah. Please get started.
Okay. Great. Well, thank you and welcome to my talk on data-oriented design for differentiable probabilistic programming. This is joint work with Maria, Younes, and Sam. So this talk is one of the reviewers described this talk as kind of like a functional Perl style talk, which I actually thought was, I didn't think of it in that way, but it's kind of accurate, which is that this talk is basically about a technique or a trick for taking a data structure that was originally formulated in a lazy language, Haskell, and making it work in a strict language. But the why do we care about this? Well, the overall motivation is that the data structure in the lazy language was is the key component for lazy PPL, which is a probabilistic programming language for non-parametric statistics. So, like backing up a couple layers, I want to start by talking a little bit about why do we care about non-parametric statistics. So what is non-parametric statistics? So it's kind of a confusing name because there is still a parameter space conceptually. It's just that sampling from the parameter space calls rand unboundedly many times. So it's the parameter space is just not Rn. That's all it means. So an example of this would be piecewise linear regression, where when you do piecewise linear regression, you're sort of trying to fit data points with a piecewise linear function, but you don't know ahead of time how many pieces. And in theory, it could be unboundedly many pieces. So that's why it's a non-parametric problem. So why non-parametric statistics? Well, in typical Bayesian inference, you sort of take a fixed model and you infer its parameters. But what if you are unsure of the model? So in epidemiology, we have these things called Petri nets, which represent sort of they're models for epidemiological processes. They involve like populations and transitions. And you can take one of these models and try and infer its parameters. But what if you want to infer the model? Well, then you need a non-parametric statistics approach. And also, if you're doing stochastic differential equations, when you have an adaptive SDE solver, it might call rand. You don't know how many times it's going to need to call rand. So now I'm going to get into the data structure. To give motivation for the data structure, I'd like to contrast lazy PPL with a classic Haskell PPL. There are several Haskell PPLs which sort of work on this basic design, which is that you have a probability monad and it's given by the state monad over a list of doubles. And so uniform here would just take the first list of doubles. And you do this so that you can in Metropolis Hastings or Hamiltonian Monte Carlo or et cetera, you can sort of vary the doubles as you do MCMC. The problem with this is that when you sequence things, the first thing has to complete fully before the second thing can run, because you have to know how many things the first thing ate. So the lazy PPL gets around this by having a different monadic composition. So now prob kind of looks like the reader monad, but notice that it uses split. Instead of passing the same tree into both processes, it splits the tree and passes one thing into the first and the second thing into the second. We'll talk about exactly how tree and split are defined in a couple slides. So here's an example, though. What does it look like? Well, we can sample a linear function by sampling its slope and its y-intercept. Then we can sample a stream of linear functions, a lazy stream. So this will only, it'll keep using things as long as you actually ask for them, but it won't give the whole list up front. And sort of the great thing about lazy PPL is that, like, even though this linear stream needs like infinitely many random values, you can still sequence them. So you can have two linear streams, and because they're sort of working off of independent halves of the tree, they won't interfere with each other in a way that they would for the sort of the traditional PPL design. So how does this work? Well, it's this tree is this thing called infinite rows trees. So basically, an infinite rows tree consists of a double and a stream of infinite rows trees. And then a stream of infinite rows trees is just the classic. It's like a cons list without the nil case. And this is what it looks like to split. So you take it, you can cut off the first thing in the stream and return that as one tree, and then take the double from the tree and add it to the rest of the stream to make a new tree. Okay. How do we actually make these? Well, you make these, you can sort of lazily construct an infinite rows tree starting from a splittable random number generator. So if the random number generator has this interface, you can make a uniform random number from it, and you can split it. Then you can create a rows tree by these two mutually recursive functions. One creates a tree by sampling a uniform and then sampling trees, and the other creates a stream of trees by sampling a tree and then sampling a stream of trees. Crucially, with different random number generators. The thing to note for later is that sort of, if you imagine a lazy thunk, which has over rand tree or rand trees, it only has to close over the random number generator. Okay. Now we're gonna take the lazy data structure and make it work in a strict language. We're also gonna make it work more efficiently with data-oriented design. Data-oriented design is a term that I think comes out of video games, but it's basically just kind of a philosophy for how to make things go fast. And how do you make things go fast? Well, you use memory in a way that is easy on your CPU caches. So you put similar things nearby to each other, and you make your data structure small. So I'm going to show how to use these principles to transform the lazy data structure into a high performance strict data structure. So the first thing is, well, we have trees and we have streams of trees. So let's put, instead of spewing these all over the heap, let's put these in vectors. And this looks like this. Now, this first take one doesn't actually work because we have no thunks. So this would have to be an infinite thing. But the basic idea is that we have these trees, and then they point into the tree streams by index, and then the tree streams point into tree and tree stream also by index instead of pointers. Now, to add the thunks into the mix, we can sort of manually implement the Haskell thunks by having, remember that the state of the closure for the thunk is just a random number generator. So we can store all of the states of those closures in a vector, and then a thunk either points into that vector for the unforced case, if it's an unforced thunk, or it points into either trees or streams when it's forced. So then we just take the same structs as before, and instead of having indices here, which are U-sized, we put thunks. Then the last step is to make thunk really small. So here, if you do the calculation, thunk turns out to be 16 bytes. Here it is 4 bytes. That is 4 times smaller, which is great. And then we also do a array of structs to structive arrays translation, so that which also for alignment issues that just makes everything more compact. This is another like wisdom from data oriented designs. So instead of having a vector of structs, we take each field and put it in a separate vector. And what does this look like to actually use? It's actually, I won't show all of the techniques, but we can wrap this in a fairly ergonomic interface to use from Rust that essentially just involves passing around this tree pointer struct. You can call this tree pointer trawl.normal, and it'll sort of sample normal random variables, and you can also split it. This sort of takes advantage of Rust's ownership system, where if I passed the tree into this first sample lin, I wouldn't be able to use it for the second. So instead, I sort of split off, which also mutates the tree in place, so that I can sample twice. And actually, it turns out with some clever things that I won't get into, you can replicate some other things from the Haskell, like the piecewise linear functions. Okay, so is it faster? The big question. Well, we're pretty sure. Basically, we've tried Metropolis Hastings on piecewise linear functions. The Haskell version runs in 5 minutes. The Rust version runs in 2 seconds. I think that's pretty good. But benchmarks are hard. Apples to apples comparisons are also hard. The Haskell might be doing slightly different things, so we have to figure it out. But preliminarily, it looks pretty good. But more importantly, when I look at the profile, the managing the tree is not the majority of time. The majority of time happens in the actual sampling and Metropolis Hastings algorithms. So that's good enough. The other thing is that beyond whether it's faster or not, it enables this technique from lazy PPL to be used in more traditional scientific languages, which have libraries for ODE solving, autodiff, etc. So Rust and also C++ and Julia. And it opens the door to algorithms which you need to iterate over the observed sites. Because in Haskell, you can't tell whether a thunk has been forced or not. But now you can actually introspect and tell whether the thunk has been forced. And in the future, so we have already, in fact, integrated this with a reverse gradient autodiff engine. I don't have time to go into that. On top of that, we hope to integrate it with Hamiltonian Monte Carlo, but non-parametric Hamiltonian Monte Carlo is still an open research question, which I think Maria will give a talk on. Either she's already given it or she will give it. And then the final extension would be to use this data structure in the backend engine for a high-level DSL, which the Rust interface is already fairly ergonomic, but it would be convenient to not have to pass around the tree pointer everywhere. So that's it. Thank you.
Gilwood, thank you. So are there any questions in the audience? Maybe, okay. I can ask a first question.
Yeah.
So, okay, I think you kind of covered it, but I mean, the abstract says the thing, the work was motivated by aiming, you were aiming to reduce memory usage and things like that. So have you achieved these memory reductions? Or maybe another way of asking this, were you, did you have some theoretical expectations about the sort of memory reduction you can achieve with this sort of thing before starting the work? And did you see these actually source of reductions? Sorry, I'm my jet lag is hitting me. I have to let you know. Yeah.
So I would say that there's sort of 2 sources of memory reductions.
Yeah.
One would be the actual sort of sorry, there's a bit of echo. The one source of memory reduction would be that it's the tape itself is smaller in memory. But another source of memory reduction is that we can reuse the tape memory for successive runs in MCMC. So in like lazy PPL, there's sort of unbounded, or it's like the garbage collection can't you either have to garbage collect the old things, or if in lazy PPL, often they end up being held onto by garbage collection. So when you have it in Rust, you can actually have you can guarantee that it's constant memory usage over the MCMC run, as opposed to Haskell, where if you get lucky, it might be, but there's sort of always bugs there. So I would say of the two things, the second one, where you can guarantee over the course of MCMC that the memory use is just constant, that's more important than actually. I mean, having the memory be smaller means that it fits into cache more, which is great. But the second one, I think, is the more important thing.
I think there are like a couple of questions. Maybe
Yeah, hi, this is Steven. So I had a question about exactly what Rust's ownership model is doing here. So, I was curious because you have this splittable resource here, this random number generator. And in Rust, you need to be very careful about this, especially if you have a mutable resource and you're splitting. And I was just curious, to what extent did Rust's ownership model agree with or not agree with how you were manipulating the resources as they flowed through this?
That's a great question. So there's actually unsafe happening here under the hood, because these pointers are like, when I split it, it's actually pointing mutably into the same structure as the old pointer. But it's like I make the interface so that the sort of only mutation of the structure is evaluating thunks. So even though it looks like there's concurrent mutable accents, like it's actually fine. So Rust's memory model was actually, or like ownership was actually a hindrance here, because I did have to drop down to unsafe. But once I only exposed these safe operations, then the ownership was kind of nice, because it enforces the fact that you have to split when you call a subprogram, which is like, it doesn't have monads, but you can enforce that the monadic composition from Haskell is what you have to use when you're calling subprograms, which I thought was kind of interesting.
Thank you.
Thank you.
Hi, Owen. Thanks for the talk. So one part of what makes lazy people lazy is the use of these rose trees. Because if you tried to use a different randomness monad in Haskell, then it would have, inside of the monad, you'd have to resolve things in sequence. But another part is just that Haskell is lazy, which means that user programs can do things like use infinite data structures and stuff like that, which is what a lot of the examples in that affine monads paper were sort of getting at. So how could you program like that in your Rust DSL? Is that a goal of this project? And if so, have you thought about how to get that sort of user-facing laziness into the language?
Yeah. Is that Alex, by the way?
Yes.
Okay. I can't see you, but I can recognize your voice. Hi. So that's a great question. The answer is yes. Basically, you can make like lazy data structures, which so for instance, let's say like a lazy infinite list of normal random variables. You can do that by storing having a struct that stores a pointer to the tree, and then sort of uses that subtree, that pointer, that it's subtree, to like get more stuff on demand and memoize them. So it's like a struct that you can you can. It has a vector of like the things that it's already got in it. And then if you ask for something that it hasn't got yet, it'll just like expand the vector until it gets that, and then return that. I don't know if that made much sense, but it does work.
Cool. Thank you.
Thanks. I think this is all the time we have for questions. Thank you very much again, Owen. So let's thank Owen one more time, please. All right, so we will move on to the next talk, which is Kartik Chandra, and the title is a domain-specific probabilistic programming language for reasoning about reasoning. We are running slightly late, but I think it's fine given all the issues we encountered, and it's good to give people a chance to interact.
I'd
yeah.
like to play some sound at some point.
Yeah.
Can we just verify that works?
Let's try.
It should be playing some more sound.
Oh, okay. We tried it in the coffee break. It was working, right? Sorry, can we test the audio from the laptop somehow?
So it's not working now?
No, it's playing now, apparently. Yeah. Okay. Can you start again? Yeah, I don't see it on the screen before. Like when we tried it in the coffee break, we were getting these like bars. Okay. No.
How about now? Oh, yeah, there
Okay,
it is.
that's good.
All
yes.
right.
So let's I don't know. Let's give this 5 minutes maybe to resolve. So what sort of audio do you have about reasoning? It's very
Yeah, well, that's
curious.
for me to know and you to find out.
Okay.
No, it's a surprise. I think it'll be worth it.
Oh my God! So where are the people who were here the whole time? Get the pretzels. Do you know where they might be? Okay. Okay, so the AV people left us for some reason. Maybe we can try to randomly push some buttons. Not so randomly. Okay. All right. So, are you still playing that?
Yeah.
Okay. So let's try to see inputs.
If you're all super duper quiet, maybe.
No, the audio input is not correctly selected. Okay, they're back.
Yeah, it says it's outputting to this device, which is what it said a little bit earlier.
Can we try again?
Yeah, it should be playing sound like right now.
Yeah, we get the signal here. I think that's working.
Okay.
Clouds, where the soft winds blow.
Almost there.
Far from all the noisy crowds, where the earthbound go. Your wings have brushed against the star, boundless were the skies. You may have flown too high, too far.
It's looking super complicated.
Seldom wise. Don't
Things
you
happening
see,
here.
Meadowlark, though you try, your call won't turn another lark in flight. He has gone, Meadowlark. You can sing your song until the dawn brings light. Sing with all your might.
All right, there it is. Thank you so much for making that work. I really appreciate it.
Is it good to go? Okay, I think we are good to go. Yes?
All right, great. Thank you all for bearing with me. I'm just going to get started. I wanted to start this talk by playing a game. It's a game that comes to us from the philosophy of linguistics, and it's called the Lewis one-word reference game. And here's how the game works. You're sitting at a table, and there's these three things on the table. There's a pink circle, a green circle, and a green square. And across from you, your partner is sitting there, and your partner has been randomly assigned one of these three objects to communicate to you. And if you successfully pick the correct object, then you both get a prize. But what makes this game interesting is that your partner can only pick one of four words. Your partner can either say round, green, square, or pink. So for example, suppose your partner says, can you please bring me the square one? Just point, you guys, which object would you pick? Yeah, okay, so strong preference for the green square. Similarly, if your partner says, well, can you please bring me the pink one? Again, can you guys point? Yeah, great. Strong preference for the pink circle. What if your partner says, can you please bring me the green one? This one's a little bit harder, right? Because the green circle and the green square are both green, and so like, what are you gonna do? But, and this might be surprising to some of you, people generally have a pretty strong preference for picking the green circle over the green square. And this is like a real phenomenon. It's robust, it's replicable. Here's some data from a replication by Ching and Frank in 2015, where they found that about twice as many people prefer the green circle over the green square when we asked them. So, okay, what is going on here? What is breaking the symmetry between the two green objects? Well, one way to think about this is to reason about how the two players in this game might be thinking. So I, the listener in this game, well, when I'm faced with the word green, there's really not much I can do. I'm ambivalent between these two shapes. What about my partner? Well, let me think about what my partner is doing. My partner actually has the same problem. Say my partner is trying to communicate the green circle. She could say green, which is ambiguous, or she could say pink, sorry, round, which is also ambiguous. So she's also in the same pickle. Okay, so what can she do? Well, my partner has available a trick that I don't have, which is she can start recursively thinking about me. She can say, look, Kartik's a smart guy. He knows that if I were going to communicate the green square, I would say square because it's unambiguous. It's totally clear what I mean by square. So given that I'm saying this risky, ambiguous word green, Kartik should be able to figure out that I'm trying to communicate the green circle and not the green square. Did you all follow that? Great, lots of nods. Good, so this kind of reasoning about other people's reasoning is called the Rational Speech Acts framework, and it has been astonishingly, hugely successful in computational linguistics to try to explain why people assign meanings to the words in the way they do. And actually, it's not just linguistics. A wide variety of disciplines across computer science and even beyond computer science have tried to build models of how people reason about the world in terms of reasoning recursively about other agents under uncertainty. So it's not just linguistics and NLP, it's also collaboration, collaborative robotics, it's also pedagogy and education, it's also expression, graphics, art, and HCI, and more broadly, any field of study that's concerned with how we coexist in a society, for example, behavioral economics, law, policy, AI ethics, these disciplines all consist of people thinking about how we think about other people. And these disciplines all have people who are trying to write computer programs that can reason in the same way that people are. I would submit to you that what we are looking at here is a whole programming paradigm, a paradigm that I've been calling the recursive rationality paradigm. And what do I mean by rationality? Well, by rationality, what I really mean is Bayes' optimality in the face of uncertainty. And so it's not just a programming paradigm, it's a probabilistic programming paradigm. And in fact, like maybe 2 hours ago, you saw a talk right here at LAFI. That's the opening slide, which showed how you can use probabilistic programming languages to implement this kind of nested recursive reasoning about other reasoning and these kinds of theory of mind domains. Okay, so that's the good news. The bad news I am here to deliver to you is that based on my many years of experience building models like this and collaborating with people in computer science and beyond making models like this, I've come to the conclusion that it's really difficult to program in this programming paradigm. And I want to give you a very clear intuition for why that's the case. So I'm going to play you a little video clip that will hopefully like start squeezing your intuition a little bit, like get the wheels turning. Here's the clip. Just watch this and enjoy.
Joey, do they know that we know?
No.
Joey?
They know you know.
Oh, I knew it!
I would say, thank God, everybody knows it's finally over, but that hasn't been working for me.
Oh, I cannot believe those two. They thought that they could mess with us? They're trying to mess with us? They don't know that we know they know we know. And Joey, you can't say anything.
Couldn't if I wanted to.
Okay, so I hope from watching this you came to the same conclusion I did, which is that the reason programming in this paradigm is difficult is actually the same reason that programming in any paradigm is difficult: correctness and efficiency. And I'll tell you what these problems are one by one. The problem with correctness is that when we talk about people thinking about other people, we have this beautiful, rich vocabulary of words like believe, think, see, do, know, want, imagine. But when it comes down to brass tacks, when you're writing your probabilistic program, the verbs you get to use are sample, infer, and condition. And so as a programmer, you're constantly translating from believe, see, think, do, know, want, imagine to sample, infer, condition. And who knows if those semantics are preserved. And if they're not preserved, you might end up with all sorts of really subtle, hard to catch bugs that are related to like deep notions of what it means to be an agent. And if you're curious what those bugs are, you can ask me at lunch, or you could stick around after lunch when Yiju, who's sitting right there, will give a talk about exactly this kind of bug. That's the problem with correctness. The problem with efficiency is that when you're thinking about people thinking about the world, there's this sudden combinatorial explosion in possible world states. Not just states of the possible real world, but also imagined states of worlds that imagined people or imagining other people might be imagining. Things rapidly get out of hand. And so in practice, what happens is that, for example, a behavioral economics PhD student might make a model of an agent reasoning about another agent, and then fitting that model to data might literally take days on their laptop. And I think this is fundamentally holding up the progress of science in many disciplines. And the reason I think that is because if you're a grad student and it takes you 3 days to fit your model, you go to science in a completely different way than you would if it takes, let's say, a few seconds or even a few milliseconds to model. Okay, so that's why programming in this paradigm is difficult. These were some thoughts swirling in my head around this time last year, actually, when I went to a conference. It's the annual meeting of the Society for Philosophy and Psychology, and it's just crawling with people who build models like this all the time. And I had lunch with a bunch of them, and we vented about the situation, and then we came to the conclusion that we needed a new tool. We needed a new kind of abstraction, a new kind of language for building these models. And that language came to be called MEMO. MEMO, which stands for mental models. So MEMO is a domain-specific probabilistic programming language for programming in the recursive rationality paradigm. And here's what MEMO does for you. On the correctness problem, instead of being a language architected around sampling random variables, it's architected around having agents make choices. And suddenly there's this nice impedance match with our intuitive vocabulary: believe, see, think, do, know, want, imagine. On efficiency, what MEMO does is recognize that if you have multiple possible worlds, well, they're all independent, and so you should be able to analyze them in parallel. And so what MEMO does is compile recursive reasoning models into parallelizable array programs in JAX, which can then run really fast on modern hardware. Okay, so let me give you a demo of MEMO in this one-word reference game. So MEMO is embedded in Python, and so to get started, you just write some Python, right? Remember, there were these 3 objects on the table. I'm going to call those reference, use a little bit of linguistics jargon. So let's say R is the set of reference, U is the set of utterances. These are the words that your partner is allowed to say. And let's write a little function that tells you whether an adjective is consistent with one of these references or not. All right, that's Python. Now I'll write some MEMO. MEMO is fundamentally an array-oriented language. And here, the array we want to generate is the conditional probability table that's exactly the same thing as what I showed you earlier, the data table from Ching and Frank. So conditioned on a listener hearing the utterance U, what is the distribution of reference that they're likely to guess? That's the table we want to generate. Okay, how do we generate this? Well, remember, our model here is that the listener is thinking about the speaker. And in MEMO, the way you write that is you say, well, the listener thinks. What does the listener think? The listener thinks that the speaker is randomly assigned one of these references, and then the speaker chooses an utterance that, for now, let's just say the speaker randomly chooses an utterance that is denotationally consistent with the referent. Okay? So now we've set up the listener's model of the speaker. What happens next? Well, the listener observes the speaker's utterance, and then the listener makes a bet. The listener guesses or picks an object on the table, and then we want to return the distribution over the listener's guesses. That's it. That's the whole model. And when we run this, we get out, as promised, a table. And for example, you can see that for conditioned on the utterance square, the model is pretty confident that people are going to guess the green square. But if conditioned on the utterance green, people are unsure about whether it's the green square or the green circle. Now, if you've been following along carefully, you remember that actually this is wrong, right? People had a preference for the green circle over the green square, so I must be missing something. Well, what I'm missing is that so far I just have the listener thinking about the speaker. What I'm missing is that the speaker is also recursively thinking about the listener, and probably you're thinking this is about to get really hairy, right? Because now he's going to have like a speaker thinks, listener thinks, like things are going to get kind of messy. But actually in Memo, it's not so difficult. It's actually just a one-line change. All we have to say is now the speaker chooses an utterance based on a recursive call to the model of the listener. And OK, fine. If you have a recursive call, well, firstly, you need to actually make the recursive call. That's where that happens. And then you need to thread through like a little bit of state to make sure that your recursion terminates. That's this new t parameter. And we'll say that the speaker actually picks based on a softmax over the listener's probability of guessing the thing correctly. So we'll have like a softmax sharpness parameter. But that's it. And when we run this model, indeed, there is a preference for the green circle over the green square, as we expected. And you might say, OK, fine, this was a simple game, and you wrote a simple model. Like, what is interesting or exciting about this? Well, for comparison, here is how someone would write this model before Memo. So this is code I took verbatim from a computational linguistics textbook that is doing this exactly the same model. And let me say a couple of things about this. Firstly, there's kind of something funky occurring, right? Because this model says, well, the speaker, var speaker, is doing something. What is the speaker doing? Well, then it says infer. But the speaker isn't really inferring anything. The speaker is choosing. So there's definitely something kind of funky about how the PPL is being used here. Whereas in Memo, the speaker chooses. That's the word we use. Another kind of interesting thing is this model is pretty slow to run, and it takes even longer to fit parameters. And part of the reason for that is that it doesn't really integrate with scientists' actual workflow. In fact, the way people run programs like this in practice is actually to copy and paste it into webpeople.org and run it based on their web form, which is just a difficult workflow. But in comparison, think about what it's like in Memo. The model matches our intuitive description. We use words like thinks, given, chooses, observes. It's about 10 times faster, and if you plug in a GPU, it'll just use it because that's what JAX does. You can optimize parameters by gradient descent out of the box because the entire model is end-to-end differentiable. So for example, you can find the best softmax parameter that predicts people's behavior. You can plot the data just by passing it into matplotlib. And if you wanted to use this module as part of some deep learning workflow, or if you wanted this model to itself call out to maybe a deep learning model of hearing or something, you can just do that because it's all the JAX substrate. OK, so Memo works not only on these toy problems, but on a lot of toy problems. So here's a bunch of classic demos which we ran Memo on, and we compared it to existing expert-written implementations. And generally, you get a few orders of magnitude worth of performance boost by writing about half the amount of code. But more to the point, Memo is useful for building the real kinds of models that people want to build. So folks at a whole bunch of institutions are already using Memo to build their models. A couple of undergraduate level courses in computational cognition are now using Memo as their teaching language. So it really does work for the things people want to do in the real world. That's all I wanted to say about Memo. I wanted to leave you with some thoughts to ask me about either during lunch or during the poster session. I'll give you 3 thoughts very, very quickly. Thought number 1 is, I said Memo does something about correctness, but I didn't really tell you what that meant, right? Like, what does it mean for a Memo model to be correct? I think that's a really deep question. I think, in fact, to answer that question correctly, you don't just do computer science, you have to do some cognitive science, you have to do some philosophy of mind. It's really deep and really interesting. And if you want to hear a little bit more about that, stick around for Yishi's talk after lunch, and you'll get a little taste of what we're thinking about when it comes to formalizing Memo's correctness properties. I highly recommend that. That's thought one. Thought two is, when we think about people's thinking, one of the things we think about is the process of thinking. So for example, if after this talk I came up to you and said, so how did you like my talk? And you went, it was really good. Like alarm bells would go off because it should not take you that long to tell me how good this talk was. And so people naturally can reflect not only on the conclusions people reach, but the way they reach them. And Memo has features to reflect on the inference process itself, because JAX has features to reflect on the number of flops it would take to run a computation. And I can tell you about all sorts of really interesting things you can do with that at the poster session or over lunch. The last thing I want to say is I think Memo can teach us something really interesting about the role that natural language plays in intelligence. There's all sorts of really compelling, really fascinating evidence that children can't really think about other people's thinking in the way an adult can until they learn the word thinks. And why might that be? Isn't that surprising? Isn't that, in fact, shocking? If you are as shocked about this as I am, then ask me about this, because I will tell you why I think that studying programming languages can help us understand the role natural language plays in intelligence. So that's all I have. Thank you for listening. And we don't have to do questions now. You can just ask over lunch. Thank you.
All right. I think we can take one question in the interest of time, if there's one quick question.
Well, I guess mine's a great talk.
Thanks.
I'll start with that instead of ending with it, just so you know. I guess I'm curious. Like Memo seems like a really cool formalization of a lot of the ways that the team, these modalities that appear in natural language, and then kind of the formal models that cognitive scientists have come up with. I guess, also in other areas of computer science, we have really rich and in many ways much more proven tools for talking about not necessarily the beliefs of other systems, but of other agents, but of their contents or their resources. Like we have all sorts of formalisms for distributed computation, like the actor model, or choreographic programming or multi-party session types. I'm wondering in particular if you have any thoughts on how both Memo in particular and these ideas in general from the cognitive science side of things relate to these ideas in distributed systems.
Yeah, thank you. Okay, so that's a fantastic question, right? The question essentially is, well, I developed this language that's about reasoning about the contents of minds. And that is necessarily rooted in some sort of biological reality of how brains work and how brains think other brains work. But there's also all sorts of other things that are kind of mind-like in the sense that they have contents that may or may not be accessible, but you might get information about them. So for example, distributed systems work this way. Various things in cryptography also work this way. I think you're totally right. And I think there is a natural way in which those kinds of formalisms connect to what Memo is doing. One of the reasons Memo is built the way it is because it's inheriting a lot of the tradition of cognitive modeling from cognitive science and cognitive linguistics and computational cognitive science. But I don't think that it's necessarily incompatible with formalisms in distributed computing and in cryptography. And I think actually, in many ways, if we really wanted to formalize Memo, we could potentially do it using those tools in some like really interesting ways. So sorry, I'm stumbling a little bit because the number of things I actually want to say about this is much larger than the number of things I can like in practice say in this time. But if you want to talk afterwards, I will say like about 12 more things to you.
Sounds great. So we are running a bit late, so let's finish it here and let's thank Kartik one more time. I have two quick announcements. So I learned that lunch is served on the third floor. We are breaking for lunch until 2 p.m. The second announcement is you can sign up for the dinner. There's a sign up link. So I just wanted to remind you that. See you after lunch.
ready, and then we could also use part of the coffee break to talk about the posters and as a sort of talking point. Now we're very fortunate to have Daisy Ivanova with us. What we've done this year is we've invited some speakers who are not directly from the programming language community, but who we thought were working on some really exciting new applications of probabilistic programming ideas that hopefully can inspire some new programming language technology. So in the case of Daisy, it'll be topics related to modern experimental design that she'll be talking about. Daisy is a Florence Nightingale Bicentennial Fellow at the Department of Statistics in Oxford, and she's working on probabilistic machine learning with a focus on robustness and uncertainty quantification. She did her PhD in Oxford with Tom Rainforth and E.Y. Tay. And she has quite a diverse background as well, working in industry and internships at Microsoft Research Cambridge, Meta AI, and before that she even worked in quantitative finance at UBS and Goldman Sachs. So I'm looking forward to hearing what you have to tell us, Daisy. Thank you.
Hello. Oh, excellent. All right. You can hear me well? Yeah, perfect. All right, thanks again for inviting me. It's always super nice to kind of see what other communities are up to. And hopefully, we can exchange some ideas on, what we in the machine learning community, kind of the probabilistic machine learning community, can borrow from what you're working on and vice versa. So today I will talk to you about what we're calling modern Bayesian experimental design. I will try to, establish what we mean by traditional experimental design as well. And here's a quick agenda of what I'll cover today. So the majority of what I'll present is actually based on this review paper that we put out last year called Modern Bayesian Experimental Design, so the same title. And after I establish, what experimental design is about, I'll talk about variational approaches to designing experiments. Then I'll talk about what we call policy-based Bayesian experimental design. I will briefly touch upon kind of more advanced methods that we're developing that kind of go beyond simple parameter learning. And then I'll discuss some of the limitations in kind of our field overall and what some potential interesting directions are there for future research. All right. And just to motivate, why we care about experimental design, in a sense, a lot of, fundamental problems in science and in engineering can be described as an experimental design problem. And here are a couple of examples. So, imagine you're running an online survey. You might want to tailor your questions to the participant in that survey so that you can ask as few questions as possible and extract as much information out of these questions. When we talk about, the pharma industry, in things like drug discovery, you might ask the question, what is the most promising compound to try in kind of a drug development pipeline? And even in sort of predictive machine learning tasks, if you are building a machine learning pipeline, you might, want to use something like active learning to reduce your labeling cost and so on. So all of these things essentially constitute an experimental design problem. And I want to kind of give you a very simple example for you to kind of keep in mind as we sort of go through this presentation. If you're a physics expert on fusion, you can think about the presentation that we heard this morning from Jonathan. But if not, bear with me, and this is quite simple. So now imagine you're a behavioral economist or a psychologist, and you're trying to sort of determine people's time value of money preferences. Now, the way that this is typically done is by asking participants a series of questions of the form, do we prefer some money now or some money later? And kind of on an intuitive level, we can say that the first question, do you prefer 150 pounds now versus 100 pounds in a year, is a very bad question to ask, right? Because no human being will prefer less money later on. But if you were to ask, do you prefer 50 pounds now versus 100 pounds in a year, depending on who you ask, if you ask a poor graduate student, they may prefer money now. If you ask a professor, they might, have different preferences. So we can begin to sort of discriminate between people or the subjects of the experiment. Now, we kind of want to formalize this, informativeness of a question. And the way that we're going to do that is in an information theoretic setup. So what will constitute a good design or an optimal design will be the one that once you collect the data out of the experiment, that data will be maximally informative about the thing that you're trying to reason about or learn about. I'm going to denote the designs by Xi in this presentation. The data that we collect will be denoted by Y. And the quantity of interest, think this abstract time value of money preference parameter will be denoted by theta. And in a sort of traditional Bayesian way, we are going to introduce a probabilistic model about this sort of process or phenomena. And we are going to start with a prior on our parameter of interest, so prior on theta. And we're going to have a likelihood function that sort of describes the relationship between the outcomes of the experiment and sort of the parameters and the controls or the designs. And of course, our prior and our likelihood give us the posterior on the quantity of interest. Now, going back to our example, right? In this case, the design variable will be the tuple of the reward now and the delay in, let's say, days. The outcome of the experiment is the participant is either going to accept the delay or reject the delay, and theta will be the model parameter, right? The model is actually not super important. We have it written down here, but you can just think about it as a function that, again, sort of describes what the relationship is between Y's, theta, and designs. Now, what do we mean by maximal informative? Given that we're in this model-based setup, there is a very natural way of defining information or an information content of an experiment. And this is the information gain, right? So we have our prior. We can look at the entropy of our prior. We are going to run a design, an experiment with design Xi, observe an outcome Y, resulting in some posterior, and we can calculate the entropy of that posterior, right? And looking at the difference between prior entropy and posterior entropy gives us a kind of a metric of information gain. Now, the problem here is, obviously we don't know why before we actually run the experiment. So what we normally do to actually get an actual metric according to which we can rank experiments is to take an expectation with respect to all possible outcomes. And this gives us the expected information gain. Okay? And this concept goes back to Lindley in '56, so this is nothing new. And it's very nice, and it's very kind of mathematically appealing to work with this quantity. But in practice, it is extremely computationally unpleasant, so to speak, to actually work with it computationally. So the EIG, the expected information gain, is what we call a doubly intractable quantity, which means that, first of all, it is hard to estimate for any given design xi. It would involve sort of nesting of Monte Carlo estimators. We heard a little bit about nesting of probabilistic programs earlier this morning. And it will be even harder to optimize, right? Given that it is computationally expensive to estimate, we also want to optimize over overall possible designs. That becomes quite hard in practice to do for kind of general models. And here I have just sort of different formulations of the expected information gain. This is literally just doing some Bayes row gymnastics. Regardless of the Bayes row gymnastics that you do, you end up with either an intractable posterior or an intractable marginal, right? So what can we do to speed up the computation? Now, the key idea will be that we're going to approximate some of these unknown quantities or the unknown densities using specialized, highly expressive neural networks. You can think about them as some form of surrogate models that we're going to learn by simulating from our model. And to give you a quick example, here I have the nested Monte Carlo estimator of the expected information gain, right? So we have an expectation with respect to our model. And inside this expectation, we have this intractable marginal distribution in the denominator, which is different for every yn that we sample, right? And the simplest thing that we can do is to run another Monte Carlo estimator inside of that. And so we end up with this sort of expression here. Now, there's a couple of things to note, right? So first of all, because of the log, this thing will be biased, right? So it is biased, and it has a pretty poor convergence rate, right? So it converges as t to the minus 1/3 compared to t to the minus 1/2 for regular Monte Carlo. This is being quite slow, but it is asymptotically consistent, which is at least something. So now what we can do is essentially treat the problem as some form of stochastic regression, right? By simulating from our model and learning a functional approximation to this marginal distribution. Rather than computing it from scratch each time, we're going to use some compute to learn this Q function. And then at test time, we're just going to plug in and evaluate this function. As long as it is cheap to estimate, as long as it is cheap to evaluate, we're going to get the regular Monte Carlo convergence rate of t to the minus 1/2. Now, the cool thing is that if Q is a valid normalized density, we actually end up with a variational upper bound to the expected information gain. So I mentioned because of the log, we have even the nested Monte Carlo estimator is biased, and in this case, we are still biased, but we are guaranteed that this will give us a variational upper bound for any y and for any choice of q. That will be tight if and only if we can actually recover the true marginal distribution. Now, the bad news is that it is biased. Unless we actually recover the true marginal, there is no guarantee that we'll get asymptotic consistency, regardless of how much we actually sample. Now, the good news is that we can as easily formulate variational lower bounds as well as upper bounds, which means that we can, sandwich our expected information gain, which will tell us something about how good or how bad these approximations are. So what we end up with is, we end up with a method that is pretty good at estimating the expected information gain for any given psi, for any given design. But we actually want to optimize the expected information gain. We don't want to just estimate it. And so what we can do is, in fact, take one of our variational approximators, or more specifically, take one of the variational lower bounds that we just defined, and perform sort of a joint optimization with respect to both the variational parameters phi and the designs that we are actually optimizing over. With the caveat that the designs are continuous, but given that we can differentiate through pretty much anything these days, we can also differentiate through discrete designs with a little bit of effort. If you believe me, we can do that. We end up with a single stochastic gradient scheme that allows us to, tighten the bound and get to the optimal design in a single loop. Right. So with that, what we end up having is a quick and efficient way of getting our optimal design for a single design step. That thing fails once we actually start to do adaptive experiments. And specifically, it fails when we actually have to make the design decisions relatively quickly, as it is in this case, right? So we have a human participant. It will be rather uncomfortable to ask them to sort of, okay, wait for 5 minutes until my MC-MC converges and until I re-optimize my expected information gain. Oops. And this is what we mean by sort of the traditional approach to doing Bayesian experimental design. So we have, so we just got our first outcome, right? So now we're going to repeat the loop t times. And the first step is to actually fit a posterior, right? So we just got another data point. We're going to update our current posterior, which, at the start, this is just our prior. And then we're going to use that as a prior and optimize a new expected information gain, right? And both of these steps are expensive, meaning that we can't really run things in real time. So what can we do? And this is what we sort of, this is our solution, right? So this is the overview of our solution, how we can run Bayesian optimal design in real time. What we're going to do is actually train a policy, a design policy that we are going to sort of, we're going to use our model and do a lot of offline pre-training. Okay, so we're going to decouple the computation and the experimentation. So we're going to spend some compute on learning this policy up front before the experiment actually begins. And then once this policy is learned, we're going to take it and use it for quick and adaptive design decisions. So what is the policy? So as I said, this is just a function that will take past data and output the next design. And here it's important to sort of realize that the traditional approach that I just described is a special case of this, right? So we're not, doing something crazy. This is kind of a more general approach than the traditional approach that I just described. So what is the connection here, actually? So the traditional slow adaptive experimentation is a kind of a two-stage, expensive to evaluate implicit policy, where the stage number 1 is fit the posterior, stage number 2 is maximize my EIG. And what we're going to do instead is, define an explicit policy that will be parameterized by neural network that will take our past data, and with a single forward pass, it will produce the next design. So how are we going to train this, this network? We're calling it deep adaptive design, or DAD for short. So how are we going to train this deep adaptive design network? Well, what we want out of it is to sort of imitate or emulate the slow adaptive experimentation. And what this means mathematically is that we want it to optimize essentially the sum of the expected information gains. So at each experiment iteration, I'm gaining a little bit of information, right? And I want my policy to be maximizing the sum of incremental expected information gains. And it is actually pretty straightforward to show that this sum of incremental expected information gains is exactly equal to the expected information gain from the prior, right, from the very start until the end of the experiment, right? So this is what we call the total expected information gain, and this is just a simple corollary to the mutual information chain rule. Right? And so this is kind of more formally how we define the total expected information gain. Now, it is a function of the policy itself, right? So this is not a single design variable. This is a function that we will be optimizing over. And the objective function will be this. Again, it's an expectation with respect to our model. And inside we have the log density ratio of the likelihood to the marginal, or you can use Bayes' rule and define it the other way around as well. Now, the cool thing is that we can optimize this with one caveat that I'll get to in the next slide. But we can sample from this expectation very easily. And if we can evaluate both of these densities, we can optimize it with stochastic gradients in a single stochastic gradient scheme. Now, the only issue that remains is, again, the fact that we have an intractable quantity in the denominator. But what we can do is actually apply the variation of approaches that I just described to approximate this fairly efficiently. Okay. So we can also use simpler methods like nested Monte Carlo, right? Or we can learn a variational approximation to that quantity. In the original paper, so in this deep adaptive design paper, we did actually a pretty simple approach. So it was based on nested Monte Carlo, which gave us pretty good results already. And as long as we can actually evaluate the likelihood in the numerator, in many cases we can't. And kind of in a follow-up paper, we developed another objective that will allow us to work with implicitly defined models as well. I don't think this is particularly insightful, but just very briefly, in order to actually work with implicit models, i.e., where we can't evaluate the likelihood of our outcomes, what we're going to do is train another little neural network, another little module that will take our design histories and parameters and output a real value. You can think about it as a model that sort of approximates the density ratio, right? This or likelihood to the marginal or posterior to the prior. And so this is kind of a summary of all the different objectives that we can work with. Again, it's not particularly important what these actually mean. The important bit is that we can take them and plug them into your favorite autodiff software, so JAX or PyTorch or whatever, and maximize them with gradients in a single scheme. So going back to our example, right? So kind of with the simple model, we sort of train the policy that produces designs and sort of does that in a loop. And compared to other baselines, we are doing much, much better, both in terms of the information gain, but and also, obviously, with regards to how much it takes to evaluate these policies. So here, at the top, I have a kind of a handcrafted heuristic approach from, this is a paper from Psychology, actually. It is heuristic because it's literally based on a kind of a decision tree that was written down by hand. And for 20 questions, we're getting an expected information gain. L is the lower bound, U is the upper bound. As you can see, we're getting actually pretty tight estimates here. So we're getting 3.5 nats. And the deployment time of this is pretty quick. Again, it's a kind of a lookup table, so there is no computation involved. Then we have the traditional approach, which was, so this is the work of my supervisor, Tom Rainford, from back when he was doing his PhD in probabilistic programming, actually. So he implemented this in a very efficient way, right? With lots of tricks that were specialized to this model exactly, and couldn't really be applied to any other model. Clearly does much better than the heuristic approach, but it is much slower, right? It is running some population Monte Carlo after each experiment iteration. It is still doable to run in real time, right, with human participants, but it's a highly specialized, highly tailored model or inference scheme to the model that we're dealing with here. And our approach, the policy-based deep adaptive design, is actually performing better. And it's as quick as the heuristic one. And we found that to be a little bit strange because we're sort of learning an approximation to this expensive process. So how come we're actually outperforming the more computationally expensive approach? And there's two explanations to that. Number one, by avoiding direct Bayesian inference, we can actually, do better by limiting error propagation, right? Because if you're making small mistakes after each experiment by fitting a slightly wrong posterior, those errors will propagate through, the entire sequence of T experiments. And it might be the case that it is easier to learn to map from past experiments to the next design, as opposed to having to, do the posterior inference and then re-optimization. And the second thing is something that I didn't mention, but it is quite important, is the fact that we're learning a non-myopic policy, right? So if you remember, the traditional approach in the way that I described it involves sort of making greedy decisions. So we're only optimizing for the next best step. We're not optimizing, we're not planning for the entire sequence of T experiments, which we are with our kind of policy-based approach. All right, we started a little bit late. So, I'll just briefly show like another experiment, right? So this is an experiment where we sort of want to find these two hidden sources. And the policy, again, was trained just from simulations from the model. It is kind of doing something meaningful, kind of exploring the space and honing in when there is a strong signal. These are the quantitative results showing that, yes, we sort of do better. Right. I promised that I'll briefly mention a few kind of more advanced methodological works that kind of go beyond this simple parameter learning. So we can, define custom expected information gain criteria for things like contextual optimization. So this was work from ICMO in 2023. I have references at the end if you're interested in looking into it more carefully. We can sort of expand our parameter space to also include the underlying graph structure as opposed to just learning about parameters. So there was some work that we did in sort of active causal discovery, and also in sort of Bayesian active learning, where we can actually define better objectives for the purposes of prediction, rather than for the purposes of learning about, let's say, parameters in a neural network, which we generally don't care about. All right, and with that, I kind of want to, I guess, share some of the limitations with this community that I think this community can be of great help with. And I think the biggest one is the fact that we have developed all of these computational methods, and we're still applying them to very toy scenarios, right? I think there is a kind of a need of demonstrating the capacity and how powerful these things can be in sort of more real-world applications. And to do that, I think the main thing currently that is lacking is proper tools. Proper tools that are flexible enough for research and also user-friendly enough for practitioners that they can experiment with. I do think that the tools and the modeling kind of go a little bit hand in hand. Right? If we have the tools, we're more likely to actually work on developing better differentiable simulators, as we saw again in the morning session. It will allow us kind of to sort of close the gap between the models that we have and how closely they match the real world, right? So kind of trying to close the sim to real gap. And as long as they're relatively easy to use, actually practitioners can also do some of the hard work in coding these models up. And on the tool side, right? So as far as I know, and I've worked in this field for like 4 years. Currently, there are none that handle the experimental design pipeline in a kind of an end-to-end basis. Of course, there are tools that can handle different parts of this pipeline, such as STAN, where we have very robust and very fast exact inference, which is very well suited to kind of the traditional Bayesian experimental design pipeline, where we sort of do HMC plus something like BaseOpt. In the BaseOpt community, they have BoTorch. I don't know if anyone has used it, but it's an excellent library. It is developed and supported by Meta, so it is quite stable and quite scalable. But it really is restricted to BaseOpt problems only. And I kind of want to highlight a project that I recently got involved with a little bit, kind of on the side. It's called Baseflow, which is a kind of a modular and user-friendly package for Bayesian workflows. They recently, I think it's not yet in prod, but it will be very, very soon. It now has sort of multi-backend support via Keras 3, so you can write your models in PyTorch or in JAX or in TensorFlow and actually, use that ecosystem to train your sort of density estimators. And finally, it sort of implements a lot of the specialized neural networks that we actually need to learn these densities to a high degree of accuracy. Things like normalizing flows and two of the very kind of state-of-the-art consistency models are already implemented. And with that, I sort of want to conclude. So in terms of future directions, I really do think we have kind of a great need for better software. And again, I actually forgot to mention the first talk that we had in the morning from bases that are also developing, tools that can help us, make use of these sort of action-driven learning of world models and so on. So yeah, I do think software is a big sort of missing piece. And then methodologically, there is again, so kind of on the closing the sim to real gap, right? So we probably need some better methodology around how we handle model misspecification. But again, I think with the better tools and the better simulators, that will become less and less of a problem. And with that, I'll stop here. I hope I didn't overrun too much, and I'm happy to take any questions.
Thank you very much for a fascinating talk, Daisy. Oh, wow. Okay, we have first question.
Yeah, really cool stuff. So I was wondering a little more about what the policy network looks like. Does it really take in the whole set of outcomes, or does it have some kind of internal state that gets
So yeah, it takes, thanks for the question. I don't have a slide showing what exactly the architecture is, but it takes the outcome and the design. So the past history of data, which includes the design and the outcome. It then, generally, we kind of want to summarize them in some fixed dimensional representation. If this is what you mean by a state, then we can think of this as a state that then gets mapped to the next the next design at T+1.
So you have something to vary the
yes,
number
yes.
of inputs.
Yes,
Okay.
yes, yeah.
I got it. Okay.
Yeah.
Thanks.
Hi, thanks for the really great talk. I'm wondering if you could give some intuition on the thing you mentioned about myopic experiment design. Like, what pitfalls can you fall into if you're only thinking one experiment ahead instead of thinking of like the whole trajectory of experiments?
Yeah, great question. So I give you the following task. I give you a stick, and I want you to break it in 3 equal parts. Right? If you're optimizing myopically, you break it into 2 equal parts, and then you're going to break it into like another 2 equal parts, which is like clearly suboptimal and not the right solution. I mean, that's the most toy thing that one can think of, but that sort of
And expected information gain has this property that you can sort of, it's like a larger space of designs to do multiple experiments than just.
Yes. Yeah.
Hi, thanks for the fantastic talk. I was wondering about the relationship between your work and curiosity and reinforcement learning and robotics. So I'm really interested in that area and ways of building robots that might take epistemic actions to learn about the world, or even meta-epistemic actions to put themselves in a position where they are then better poised to learn about the world. And that seems closely related to optimal experiment design. So I was wondering if either there are ideas from that field that have influenced your work, or whether there are ways you think your work could influence that field.
This is a great question, and I should say I'm also interested in this stuff. So we should, we can chat afterwards. Currently, I think the fields are a little bit detached. The way that I think about Bayesian experimental design, it is as a special case of reinforcement learning, right? We can formulate this as a reinforcement learning problem, but then what cannot be formulated as a reinforcement learning problem. So for sure, there are things that we can sort of borrow from RL to inspire better algorithms and better methods in BED. But yeah, I'm happy to chat more after this. Thank you.
Okay, we have one final question here from Setup.
Thanks. I'm also interested, so let's all chat.
Yes.
So in the talk that Jack gave this morning, he showed some of the world modeling stuff that we're doing. And we're going from kind of the passive case to the active case, where we want agents which act in the world and then learn about how the world works. And when you think about those kind of domains, the experiments, at least the high-level experiments that you think of, are very much tied to your current model of the world, right? So you might think, okay, the thing I'm going to try right now is to press this button or press that button, but that already requires that you've kind of committed to the idea that these things are buttons, right? Which is, a belief which might be true or might not be true.
Right.
And so this puts you into kind of an interesting experimental design phase where it's not just even a finite set or even an infinite set of kind of well-described experiments that you can do. Like your experiment is kind of contingent on your current belief about the world, which is uncertain. So I just wanted to know if you've kind of seen that in other areas that you've worked on, or have any thoughts on this kind of problem.
I think this closely relates to, I guess, I don't want to call it model misspecification necessarily, because like there always is some form of model misspecification, but what you are, I think what you are describing is something like uncertainty about the model itself, right? And sort of, yeah, how do we handle that in this framework? Is this correct?
So yeah, so uncertainty about the model, but in particular, that affects the possible experiments that you have at your disposal.
Right. So are you thinking sort of model discrimination plus learning, parameter learning plus model discrimination, something like that?
Something like that.
Yeah, but I guess, you know, but then it's like, do you have all the models, right? And you clearly don't. And so, yeah, I think it becomes quite complicated. I guess the closest that I've sort of worked at, and again, there's plenty of, you know, assumptions that go into these frameworks, but, you know, sort of the causal discovery work that, you know, as long as you assume causal sufficiency, yada, 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 you know, things will work out. But I think it's like, how do we go beyond these assumptions, which clearly don't hold in sort of the world that we live in? So yeah, I think we should also chat afterwards. I think it's very interesting. So yes, thank you.
Great. Thanks so much. Let's thank Daisy one more time. And now, if all's well, we have Yizhu Zhang telling us more about the memo programming language, particularly its semantics. So it's tying into the talk from before lunch by Kartik.
Okay, right. So FOMO, a formal model of MAML. So hopefully you might still remember this one-word reference game that Kartik introduced this morning, right? And also this MAML program that models how a speaker chooses words to effectively communicate a reference to a listener, and how the listener makes inference of the speaker's true intention. Okay, the design of MAML offers a range of features and benefits, as Kartik has already told you. It allows more concise, intuitive modeling. It leads to like 10 times faster code. It integrates well with a scientist's workflow, right? So on and so forth. And just to emphasize the benefits to modeling, let's consider how this one-word reference game can be modeled in a more standard probabilistic programming language. Okay, so, and this can be done using this feature called nested inference, which is available in languages like WebPeople. So for example, here I have modeled the listener in WebPeople as a function called L. Right? This listener reasons about a speaker, by calling a mutually recursive function called S. In the listener's mind, the speaker makes two choices, R and U, okay, a true referent R and an utterance U. And the speaker chooses an utterance such that it describes that referent. Okay, that's expressed by this conditioning statement. And the speaker also prefers those utterances that increase the chance of the listener making the right guess. Okay, and that's expressed by that factor statement there. So if the listener hears the speaker say green, right, then we'd expect that the listener is more likely to infer green circle than green square, because if the speaker really meant green square, then they could have just said square instead of green. Okay. But this is what we get if we run this program in WebPeople. Okay. So the histogram here indicates that the listener cannot really make a guess between green square and green circle. Right? That's surprising, because that goes against our expectation. So what's going on here? The problem is with a subtle bug that I introduced into the listener's model of the speaker. The factor statement here has the intended effect of making the speaker prefer an utterance that increases the chance of the listener making the right inference. But it also has an unintended effect. That is, it also means the speaker prefers a referent that is easier for the listener to guess. But which referent the speaker chooses ought to be independent of the speaker's reasoning about listener. The speaker chooses an utterance for a given referent. Right? They shouldn't be choosing a referent and an utterance simultaneously. And this bug can be fixed by carefully adjusting the scope of nested inference here. And more specifically, I can fix this bug by moving the speaker's choice of a referent outside the enclosing nested inference. And now if we run this program again, we get the expected results. Okay. So all this is to just to show you that it's very easy to make mistakes when using nested inference to model rational agents. By contrast, the mammal version naturally avoids this pitfall. It doesn't even have a nested inference construct to begin with, right? So it's hard for the mammal programmer to inadvertently introduce dependencies that violate the principles of agency. Okay, so that's all great. But how should a programmer reason about programs written in mammal? Like, what is the semantics of mammal programs? We know mammal is designed for modeling nested reasoning, but it doesn't even seem to have a nested inference construct, right? So now hopefully you're confused at this point. And in this work, we aim to give a formal semantics to the mammal probabilistic programming language. We want to capture this kind of complex computational phenomenon in precise mathematical language. So the central data structure in the mammal semantics is this thing called frame of mind. A frame tracks an agent's beliefs along with that agent's beliefs about the other agent's beliefs. And stepping through a mammal program essentially evolves a tree of frames. So in this sense, the state of the program here is really the frames of minds of the agents. So let's step through this program for the one-word reference game. Initially, there is a root frame. Okay? This root frame contains only the two choices U and R, which are bound by the two axes declared in that model's header. And these choices are known to this special root agent. And this root agent has no uncertainty about the values of these two choices, U and R. The first statement of this program introduces an agent called listener. So a new listener frame is created, and the root frame contains a pointer to this new listener frame. The listener, in turn, reasons about an imagined speaker, right? So a new speaker frame is created in the listener's mind. The listener frame contains a pointer to this speaker frame. The speaker then makes two choices. So the speaker's frame contains two variables, U and R, an utterance U and a referent R. And these two variables, U and R, are not related to the U and R in the roots frame. The speaker is certain about its own U and R, right? And that's just because they are chosen by the speaker. But from the listener's perspective, the listener is uncertain about the speaker's U and R. All the listener knows is that the speaker chooses U and R from some distributions. And here we use yellow circles to indicate uncertainty. The next statement is an observed statement. This statement expresses that the listener believes the speaker's utterance is the same U declared in the roots frame. And as a result, the listener now has no uncertainty over the speaker's choice U. And finally, the listener chooses a referent R. This R appears in the listener's frame as a choice containing no uncertainty because it's chosen by the listener, but it appears in the roots frame as an uncertain choice. More formally, the frame of an agent is a triple. So first, it consists of a set of choices made by the current agent. And second, the frame contains a set of subframes. Each subframe corresponds to an agent in the current agent's mind. And third, the frame contains a set of equations that represent the conditions on the current agent's mind. Then we give a type system to memo. The form of statement typing indicates that statements are really frame transformers. So it's kind of like Hoare logic. In Hoare logic, you have a precondition and postcondition. A statement is a predicate transformer. And here in memo, you have a pre-frame and post-frame, and the statement is like a frame transformer. And executing a statement has the effect of changing agents' frames of minds. We further give a semantics, a denotational semantics to memo. A frame is interpreted into a product of two spaces. First is the space of the choice context, gamma, and the second is the space of measures over the subframes. Subframes are interpreted as measures because the current agent is uncertain about the agent in its mental state. We can prove this statement, which says for a well-typed memo statement, if the pre-frame is satisfied, then the post-frame must also be satisfied. Expression typing is also interesting, as the type of an expression in memo tracks uncertainty. So let's look at the typing of this WPP clause. Okay? So here the listener chooses a referent R with probability proportional to the listener's confidence that this R is the same as the speaker's true referent. Okay? It's important that this probability operator be there. If it were omitted, then the listener would have to make a choice based on the probability that they cannot even evaluate, okay? Because listener is uncertain about the true referent the speaker chooses. It would appear as if the listener could read the speaker's mind to find out the true referent, or as if the speaker could control the listener's mind to force the listener to choose their referent. So both mind reading and mind control violate our understanding about agency. So without this probability operator, memo statically raises an error at that line. This checking is done by in the memo type system by tracking uncertainty in expression typing. The typing judgments track not only the type of an expression, but also the set of choices that the expression depends on. There's also a choice typing judgment for deriving if the current agent is certain about the given choices. In the typing rule for the chooses statements, we first check if, so here we first check the expression in the WPP class is well typed. We also check that the choices the expression depends on contain no uncertainty from the perspective of the current agent. In our example, the manual type system can see that the listener is uncertain about the speaker's R, so it rejects this program. But if the probability operator is there, then the uncertainty is marginalized out, right? So the manual type system accepts this program. And we give a denotational semantics to expressions too. The denotation of an expression is a measure because an expression in general contains uncertainty. But if the agent is certain about the choices the expression depends on, then we can show that the denotation of the expression is a single point mass. Okay, so to conclude, we have presented a formal semantics of MAML, including a type system and a denotational semantics. This formalization is interesting because it gives precise meanings to a complex computational phenomenon, namely recursive mana reasoning between rational agents. And in the future, we'd like to use this semantics as a basis on which to formalize MAML's unique compilation strategy to array programs, right, and prove that this compilation is semantics preserving. We also want to explore how this formal semantics can contribute more broadly to our understanding of theory of mind with connections to deep open questions in philosophy and cognitive science. Okay, so I'll stop here, and thanks for listening.
Thanks, Shizu. Do we have any questions?
Thank you. That was really, really great and really clarifying. Can you say again what K was in the frame? Like you said that a frame has gamma, phi, and K.
Right.
So what was K, and does it play into the semantics?
Right, yeah. Right. K is really a set of equations on there are those Bayesian conditioning statements in the program, right? And the denotation so the denotation interpretation of frame doesn't really capture the K, because K is just making restrictions on the space.
I see. This is different from the observes statement, which causes something to become certain, right? Or
they're related, actually.
Okay.
Yeah.
Okay, I'll ask follow-up.
Yeah.
So you also said that phi is the view of the frames of other agents. So how deep can this nest? Is this well-founded? Does it have to stop at some point?
Sorry, what?
So phi is a view of the frames of other agents.
Yeah.
And those other agents can have also views on the frames of other agents.
Uh-huh.
So is this well-founded, or?
Oh, right. So so a frame there is really a tree where you consider the subframes. So it's a bounded tree, a tree of bounded depth.
Have you considered adding recursion to your language?
I think Cardic does have recursion in this language. It's just that we have bounded recursion, and the control flow must be deterministic, and that's the main reason why Cardic is able to compile program to an array programming language.
Thanks.
So following on the same questions, your language is first order, right? Would it make sense to take functions as arguments?
I don't think MAML supports higher order functions.
Right, let's thank Yuzhu once more. Now we have Maria Krachun. I don't know how to pronounce your name. Sorry. How do you say it?
Krachun.
Great. And she's going to tell us about a new inference algorithm for some very, very complicated probabilistic programs, specifically a non-parametric version of the no U-turn sampler.
Sorry, it doesn't work.
Doesn't work?
Nope. Maybe now.
Saw your screen
It worked
just
before.
a moment ago.
I don't know.
Do you see the screen there? Okay. Yeah, we saw another screen.
Not sure what's wrong.
I'm not sure either. It worked just for a moment ago, so maybe just wait 1 second. Yeah.
Oh, okay.
Okay, so now you just need to mirror your display. So if you go to.
Oh, no, it's okay.
Oh, okay.
I can just.
Yeah.
Okay, so hi, I am Maria Krachun. Can you hear me? Well. Okay. And I will talk about a version of the no-return sampler, which also works for the non-parametric settings. And this is a joint work with Lukong, Sam Staten, and Matthias Wagner. So first, I will briefly review Hamilton and Monte Carlo, then two of its variants, which are the non-parametric Hamilton and Monte Carlo and the no-return sampler. And then I will talk a bit about our contribution, which is the non-parametric no-return sampler, a hybrid between NUTS and NPHMC. So for a long time now, there has been a dream to develop general-purpose inference algorithms that work seamlessly for universal PPLs. This is especially challenging for non-parametric programs where the number of parameters is unknown or bounded. So for example, take the clustering task where you don't know how many clusters you're going to have in advance. And I think Owen already gave some motivation for non-parametric statistics. So yeah, this is very challenging. And our focus is on Markov chain Monte Carlo methods, which estimate complex probability distributions by generating a sequence of samples through a Markov chain. And these distributions are usually defined on an infinite sample space. So our algorithm, non-parametric NUTS, is going to bring together two very different axes of development in probabilistic programming. So on one hand, NUTS is at the heart of the standard probabilistic programming language, and it works out of the box without needing to be tuned, unlike HMC. And NUTS has played a very important role in the large scale of use of complex Bayesian statistics across multiple sciences, and yeah, it's quite popular. However, NUTS is not designed to work in the non-parametric settings. On the other hand, NPHMC makes it possible to use Hamilton and Monte Carlo in the non-parametric setting by dynamically extending the traces when it is needed. So our aim is to build on that and to achieve non-parametric NUTS, yeah, which is a version of NUTS, which can be applied also on non-parametric models. So the goal is to sample from a distribution with density D, and we can view Hamilton and Monte Carlo as an instance of Metropolis Hastings. So that means that we propose a sample and then we accept and return it with some probability given by an acceptance ratio. This acceptance ratio is very important, and it's specifically designed to preserve detail balance, which is important for proving convergence to the target distribution. So unlike other algorithms like random walk Metropolis or Gibbs sampling, HMC differs by using gradient information about the log target density, and this makes it converge much faster to the target distribution. And especially for high dimensional spaces, like other methods might take a reasonable amount of time, but HMC still works on them. That's nice. I will try to give some intuition of how HMC works. So we want to sample from the distribution D. Now imagine that we have a surface that describes the function minus log of D. And if we want to get samples from D, that means that we want most of our samples to be in the value areas. And yeah, if this surface is frictionless and we put a puck on it, then the puck will mostly go at the bottom of the valleys, and that's okay most of the time. However, once in a while we also want to get samples from the sides of the hills or the top of the hills. And to do that, we can just get some impulse with some momentum p, which is going to be random, to the puck. So now the puck can also get to the top of the hills or even change valleys. And yeah, p is an extra random variable, and it's normally distributed. So now we can propose our next draw Q by going for some time t with momentum p and see where the puck ends up and what position it ends up. Okay, so to do that, we can use Hamiltonian dynamics, and the system is described by the Hamiltonian H, which is the sum of the kinetic and the potential energy. So now we'll have states formed of position Q and momentum P, and at the end we will have draws from the distribution mu. So since we can see that Q and P are independent, we can just ignore the draws for the momentum P, and then our draws for Q they're going to be from the target density D. So that's what we want. Oh, it's falling. Is it better?
I think so.
Okay. So now the values for Q and P after some time t can be computed by solving these differential equations. However, we cannot do that exactly in practice. So we will approximate them by discretizing time. And one common approach of doing this is by using the leapfrog integrator, which simulates L steps of small size epsilon. And epsilon and L need to be user specified. So this is how one iteration of HMC looks. So we start with the position Q, then we sample the momentum P, then we apply the leapfrog integrator on it, and to account for the error introduced by the approximation for the simulation, we also have to have an accept or reject state. However, if we can control the simulation error, then the acceptance ratio is going to be very high, and that's nice because we can, in one iteration, we can end up further away from where we started and still have high acceptance, which is preferable compared to, for example, random walk metropolis, where the further away we go from the initial state, the lower the acceptance probability is going to be. So to sum it up, HMC uses Hamiltonian dynamics to propose the next step, and it's quite efficient even for high-dimensional spaces. However, it's very sensitive to the number of steps that we have, L, and the step size epsilon. So for example, if the number of steps L is too large, then we might waste computational power by exploring the same area multiple times in one trajectory. On the other hand, if L is too small, we might get stuck in some local minima area, and the gradient information is going to be less influential, so it's going to result in a more of a random walk behavior. And this is why NUTS wants to adaptively set the length of the trajectory at each iteration. So the idea behind NUTS is to choose L such that we stop the simulation when we start to head back. So in the sense of like we start to make a U-turn. And to do this while also preserving the balance, it's a bit more subtle. And it involves iteratively simulating either forwards or backwards in time for a double amount of time until we see that we made a U-turn. At the end, we'll have this trajectory of states, and we'll sample the next state according to the weights of the states. So for example, here, we start with one state, and then we choose the forward direction, and we go one simulation steps forward in the direction of the momentum. And then we choose the backward direction, and we go two simulation steps in the opposite direction of the momentum. So those are the yellow circles. And so on until we stumble upon a U-turn. And notice that we can view the trajectory as the leaves of a perfect binary tree. which is quite important. So one property that this final tree has is that we can construct this starting from any of the states in the tree. However, you need the doubling directions to be accordingly for each state. And this is important for detail balance. So as I mentioned, we stop when a U-turn was made. So how we can check this for a state Q and P, if we move with momentum P away from Q, we start to get closer to another position in the trajectory Q prime. So yeah, we just have to check this inequality. So NUTS is very clever about how the construction of the tree is made, and not all the nodes need to be stored at the same time. So that means that we also don't compare every pair of states in the trajectory to see if they made a U-turn. Only the leftmost and rightmost leaves of the tree are compared. So we saw that NUTS is a performance variation of HMC, which avoids manual tuning by setting the number of steps dynamically, that is using the doubling procedure and the no U-turn criterion. And moreover, this is done efficiently while recursively constructing the tree which contains the explored states. So we talked about HMC and NUTS. Now we'll see how these algorithms can also be applied on non-parametric programs. So for a probabilistic program, a trace is a sequence of sample values during one execution. And different runs of a probabilistic program might result in different traces of different length. And this can happen, for example, if you have stochastic branching and for loops or recursion. And since we don't know we might not know an upper bound on the length of the traces, this is what our target density is going to look now. So it's going to be defined on the union of R to the n. So now if we try to apply HMC on such a probabilistic program, during the computation of the leapfrog integrator, we'll go through multiple positions Q, because we'll make L steps, so we'll have L positions. But for some of those, it might happen that the position Q is not long enough. What that means is that if we run the probabilistic program on it, the values in the trace Q are going to use as seeds for the sample statements in the program, but they are not going to be enough, and the program will need more seeds. So in other words, we'll have that any prefix of Q is not going to be in the support of W, and this is not what we want. So we want to extend Q so that Q ends up in the support of W. And NP-HMC does that by running the probability program P on Q and then sampling the extra dimensions using the sample constructs that are encountered in the program. So at the end, we'll have that Q is in the support of W, and then we'll have to extend P accordingly to match the dimension of Q. And then we also have to extend the initial state, Q0 and P0, because it's going to be needed in the computation of the acceptance ratio. So NP-HMC deals with not long enough traces by extending it dynamically during the leapfrog integrator. And the acceptance ratio has to be carefully computed. So there are multiple ways of performing extensions. And one of our contributions includes some acceptance ratio together with the correctness proof for some of these ways of performing extensions. Okay. Yeah, so now we are going to talk about our contributions, which is NP-NUTS. And in order to combine the ideas of NUTS and NP-HMC, multiple things have to be taken into considerations. Of course, during the doubling procedure, we might need to extend the traces and also extend the other states accordingly. And then in order to sample from the next state from the constructed tree, we will need to know the weights of each state relative to each other in the tree. And this becomes tricky because the weight of the state depends on the probability of constructing the tree starting from that state. And moreover, that depends on the likelihood of the extensions that are made during the construction. And the fact that for each state we have different doubling directions that we need to take in order to make the tree makes this even more complicated. So a naive approach to this would be to just simulate the construction of the tree for every state and compute its weight. But of course, it would take way too much time. So we want to be able to construct the tree once and also not store all the nodes, just like NUTS does. So fortunately, we can do this by recursively combining extension likelihoods in order to compute the relative weights of the trees, of the subtrees. Another thing is that the no-return criterion must be modified, and this criterion should not depend on the extensions that are made, which are not relevant to a state. So as I said before, if you extend the state, you also need to extend the other states in the trajectory. But yeah, for some states, those are kind of irrelevant, so they shouldn't be included in the stopping criterion. And this is one possible way of doing it, but there are multiple others, and we're also interested in exploring them. So we hope that NP-NUTS will be effective for models with a large number of continuous parameters, as well as some of non-parametric features. And we are also interested in devising a version of NP-NUTS using laziness. So for example, implementing it in lazy people. And we also want to explore more versions of NP-NUTS. These include different stopping conditions, and these can also depend, for example, on the number of dimension changes that we made, or just how many times we extend the trajectory when we make the trajectory. So yeah, that's about it. Thank you very much, and I'm happy to talk about it at the poster session.
Thank you, Maria. We have time for one or two questions, I think.
Thanks a lot for the talk. So one quick question, I'm not sure I followed, but when you add these extensions, is it for just one step and then you restart for the next one, starting with the original dimension of your problem? Or do you keep the maximal dimensions that you ended up with so far?
So we keep the maximal dimensions. Maybe at the next, sorry, you mean from one iteration to another?
Yeah.
Oh, no, we can just get rid of them if they are not relevant. So it's kind of like marginalizing them out since they don't affect the result or the weight of the program.
Right, so the gradient that you compute at each step does not have the same dimension.
So the gradient does not depend on the kind of extra extensions, like the irrelevant ones, if that's what you were asking about.
Okay.
Any other questions? Okay, let's thank Maria once more then. And then we have our last talk of this session, which is a remote talk. We have Daniel Goodman, who's at Oracle Labs, and he'll be talking about Sandwood, runtime adaptable probabilistic programming for Java. Do we have Daniel on the remote connection? Yep. Yeah.
Today I'm going to talk about Sandwood, which is an open source Java-like probabilistic programming language from Oracle Labs. Unfortunately, I can't be here in person to present today, online to answer questions at the end of the talk. Many of you will already be familiar with the idea of probabilistic programming, but I'm going to do a quick recap for those who've not come across it before. So probabilistic programming is a way of constructing Bayesian models. Bayesian models are a form of machine learning model where the model is described in terms of the relationships between random variables. These relationships are expressed by the programmer based on domain knowledge they have of the problem they're trying to solve. Because the model is constructed with domain-specific knowledge about the structure of the problem, they have a number of advantages over solutions such as deep learning. The known structure means the model is more explainable. Also, because the structure doesn't need to be learned as it does with deep learning, it requires less data and so can work on much smaller problems. And this reduction in size reduces the latency and the cost of training the models. So that's Bayesian models. Why use probabilistic programming? Well, often it's relatively easy for a domain expert to write a model that models the problem they're trying to solve, but actually implementing that so a computer can do the required inference, etc. on it is much harder. So you'd have a description of the model in the comments, and then some inference code that's going to be used for training, and some further inference code that's going to be used for making predictions, and all three of these pieces have to be kept together, and the inference code is considerably more complicated than the overall structure of the model. and all in all this just becomes hard to maintain and hard to work with. So the idea behind probabilistic programming is to raise the level of abstraction and to have a simple language that instead of having the comments, we write the model in this higher level language, and then we use tooling to construct all the required inference code. This greatly reduces the cost of implementing and maintaining Bayesian models. Sandwood is far from the first probabilistic programming language. Its immediate predecessor within our group was Argo, which we developed in order to demonstrate that we could compile probabilistic programming languages and run them on GPUs. This time around we wanted to produce a language that was more robust and more mature so that we could actually use it inside of our products. It's designed to be familiar to Java developers so that when they look at the models they understand what's going on there and you don't end up with black boxes within the products that people don't want to touch. It's got compile time checking so that we don't end up with runtime errors that are unexpected. It's designed so that the models will form discrete components of the system, so unlike APIs which are running in a host language where you end up with potential for merging between the API calls and the control logic, with this we wanted to make sure that the control logic that affected the system's behavior based on the results from the model was separate to the models themselves. And we wanted the ability to target multiple different pieces of hardware as the operations change. So for example, you might want to run on a much larger machine when doing your initial inference versus when you're making predictions later on. Currently Sandwood can perform single-threaded execution, fork join execution, and can run on Callisto, which is an internal runtime system developed by Tim Harris. In the future we want to move on to working with the Java Vector API and to get back to where we were with Argo, running on GPUs. So what does a Sandwood model actually look like? Well, this is a hidden Markov model written in Sandwood. Please don't try and read all of the code now, the slides will be available later for people who do want to go through this. But the point is that this is very much like Java code, and so it should be very familiar to Java developers. The random variables are represented by objects, which have a method sample attached to them, and these objects are instantiated either by a call to new or by the use of a factory method as we're doing here. Points where Sandwood models differ away from Java are things like the variables are all single assignment, you can't call arbitrary Java functions, and unlike a Java class which takes no arguments, the models take an argument using a constructor syntax very much inspired by Scala and therein our earlier work with Argo. So having written the model, the compiler pipeline for it looks something like this, of which the bits that are of interest for this talk are the first 4 steps. So we start off by doing a source-to-source translation to a set of Java API calls, and we then compile the resultant code and execute it in order to build a DAG. By doing this step, we're able to take advantage of the Java compiler for the type checker, so we don't have to write a type checker ourselves. Having constructed the DAG, we exploit for all of the variables that are of interest and all of the possible traces between these variables. Having gathered all of this information, we then use that to construct the various inference methods required by the model. The output from this pipeline is a set of classes that represent the model. These include a class with the same name as the model. When instantiated, this object will be the object that the user interacts with in order to control the model itself. This object will have fields for each of the named variables within the model. These fields reference objects which can be used to get and set properties of the variables within the model. In addition to the publicly visible fields, the model will also have a private field referencing an object that performs the arithmetic operations required for the model. This object can be changed to target different hardware, with the relevant state being copied between the objects as required. We'll now look at one example of how this model might be used. So in this example, we're going to infer some of the values within the model based on some observed data. So the first step, of course, is to get the observed data, and where this comes from is entirely up to the user. Having got the data, we then instantiate an object that represents the model, and if we want to have multiple copies of this model, we can just have multiple objects. Having constructed the object, we can then set the retention policies that we want for the variables. So we want to record the most likely values for the variables within the model. So we're going to set the default retention policy for the model to be map. But in addition to this, in this occasion, we've decided that we don't want to record all the possible states that the model goes through. So we're going to set the retention policy for that specific variable to be none, so that those variables just get ignored and don't get recorded. Having set up the retention policy that we're looking for, we can then just tell the model that we want to infer values for 2000 steps, and this will perform give sampling for 2000 steps, recording the most probable values that it comes across within this chain. Having performed this inference, we then record the most probable values from the variables within the model by going to each of those variables' objects and just requesting the map value from that object. So that demonstrates very briefly what a Sandwood model looks like and how a user might interact with them. We're now going to change gears slightly and look at some of the problems that were associated with creating Sandwood. So one of the issues is that it's possible to have much more complex relationships in a Java-like language than it is in other languages which are structured to prevent such relationships. A simple example of this in the HMM model is this piece of code here, which describes how the model moves from state to state as it transitions through a sequence of states, generating the sequence of events that are observed from this model. So what's going on here is we start off at t0 and we use a random variable to select a random state to begin in. And then based on the state that we're in, we will pick a transition to another state at time step 2. And we will continue doing this through all of the different time steps so that the model is steadily moving through a whole sequence of different time steps. The problem that we run into, though, is that the states are written in 2 separate locations. So when the states are read here, it's not clear which of the random variables that the categorical that's currently reading from the states is interacting with. Is it interacting with the categorical that picked the initial state, or is it interacting with the categorical that generated the state on the previous iteration? In order to handle this, it's necessary to build a set of checks and guards that will ensure that the code for interacting with each of the possible random variables from where the state could have come from is only executed if that is indeed the random variable that the state came from. And obviously this is a relatively simple example, but because this is Java-like code, these relationships can get arbitrarily complex. So how do we go about doing this? Well, we start off with the for loop that the random variable we're wanting to find associated random variables for is currently executing in. And this loop's going to have some code that's executed before we get to the point where we want to work out what's going on with other random variables, and it's going to have some code that's executed afterwards. We then, as we discussed, have a set of traces between all of the possible points in the DAG. So in this case, we're going to have 2 separate traces, one of which is a trace from state I-1 to state I, and then up to the categorical that generated that value, and a second one from going from state I-1 to state 0. So for this example that we're going to work through here, I'm going to look at the trace from state I to state I-1. So we have the ability to create variable and scope substitutions, and we can use this in order to explore all of the possible array indexes that might have been generated. So when we go back to look at the put into the array that happens at state I at this point, of course, would have had a different value to the value of I currently. As such, it's necessary for us to be able to explore all of the possible values of I. And so what we're going to do is create a new for loop that's going to explore through all of those possible values. And that for loop is going to have a different index name, and that index is going to be substituted in where appropriate as we work our way back up the traces, so that we end up with a whole loads of different scopes nested inside of each other, each of which have a different set of substitutions which are required to be made to the code, such that the code appears to be executing in the environment that the element in the trace would have executed within. As we work our way through, then we're also able to put in guards, so we know that if this trace is valid, then the location that the value was written into must match the location that the value was read out of. So I-1 must equal I1 for this trace to be a valid trace and for this to be the random variable that we will be looking at. If there's more than one trace between 2 random variables, of course, you can have more than one. You're going to have more than one set of values that need to be compared, and this is going to require guards to ensure that the code that ultimately gets put in the inside of all of these nested for loops and nested conditionals is only ever executed once. All of this adds a lot of complexity, which we wouldn't want the implementer of an inference algorithm, for example, to have to consider. So to overcome this, we abstract it away into objects called scope constructors. So we start off with a scope constructor for the outermost for loop, and then we'd use a lambda to add in the code that we're going to execute before we were interested in this relationship. We can then pass to the scope constructor a set of traces from the location that it's currently modeling to an alternative location in the DAG. And using these traces, the scope constructor will construct another scope constructor representing this new location. So this is now the target for code that we've got marked down at the middle of all of these for loops. And we can now add code to this location once again by using lambdas. And we can continue to add code to the existing location by passing more lambdas to the original scope constructor. And we can nest this arbitrarily deeply. And so the user never actually sees what's going on in all of this. All of this code is generated and output without the user ever being aware that it happened. They just say, I want to run this code only if there's a relationship between this random variable and this random variable, and everything else is handled on their behalf. People will, of course, have noticed that the big problem with this is that we've now gone from something that should be a constant time operation because we've only got one possible path to something that's going to take order n times to search through all of the possible indexes. And this, of course, will only get worse as we end up with more and more nested loops for longer and longer traces, with our execution time being exponential in the length of the trace. The good news is this code can be effectively optimized. So the first observation is there is only one value of I1 that will ever satisfy the guard of the conditional. So we can just declare I1 as that value, and instead of having a for loop, we can have a conditional that checks that the value of I1 is one of the steps that the for loop would have reached. Some of the guards within this for loop can then be removed. So the one that checks that we land on the appropriate steps is trivially true, and with some bounds checking, we can get rid of the upper bound because that's also trivially true. So this finally leaves us with the option of substituting in the value of I1 into all the rest of the code. So we change the substitutions when we're updating the code, and we now have a guard that simply says that I must be greater than or equal to 2 for this random variable to be reachable. And so we've gone from some relatively complex, expensive code to something that's clean and efficient to run by applying a simple set of optimization rules. Going back to our HMM state transition model though, say we're at state 3 and time step 3. We may have got here by this path, but for a lot of the computations that we're going to want to do, what we really are interested in is the probability of getting here by any of the possible paths. And so that's added into Sandwood via the ability to say sample distribution. So we've taken the code that we showed previously, and now we've just changed it so that we're doing sampling a distribution instead of sampling a single value. This is applicable to all finite distributions within the language. The handling of sampling distributions relies heavily on the ability to detect relationships between random variables and is included within the abstractions that mean that the users don't have to think about how all of this work is done. They just have to think about the inference algorithms they might want to write. So in conclusion, Sandwood is a JVM-based probabilistic programming language that's designed to be familiar to Java developers. It's able to adapt to different runtime environments. It outputs encapsulated models which have clean separation between the model and the application code. It's open sourced and available at sandwood.org. And we are recruiting both full-time and internship roles, so if you're interested in one of those roles, please do reach out to me. Thank you very much, and I'll now take any questions if there's time.
Do we have any questions for Daniel? Okay, I have a question.
Okay.
I'm wondering. I've seen sort of similar things before. I think in the context of trying to do exact inference for discrete variables in Stan. In that project, we ended up trying to build vector graphs or DAGs out of our sort of imperative Stan programs, which are somewhat similar to your Sandwood programs, it seems. And I guess the problem we ran into then is that, if you have array indexing like you have in your HMM model, then you get that the structure of the DAG or the vector graph is only known at runtime. And we wanted to do everything as a compile time transformation, and then we couldn't figure it out. And I'm wondering, does your system handle these DAGs at runtime? And does that mean that you can really do things like a sum product algorithm or like an efficient exact algorithm on some vector graph or DAG representation that you derive at runtime by jitting maybe? Or
So the way we get around that is I seem to have an echo, sorry. The way we get around that is by having when we create the traces, we look not only at all the puts that have happened to the array before we got to our current location, but also at all of the possible puts that could happen afterwards in the array. So we actually end up, whilst it is a DAG, because it's got this extra scope information around the nodes, we're able to build a bigger set of traces than you would be able to get out of the DAG normally at compile time. And so normally you would end up at runtime having to get this extra information because you don't know how many times you're going to end up unrolling the for loops. But because we build these extra traces in of, well, this information could have come from later in the DAG, we're able to overcome that. The one limitation we do have on that, though, is you can do, for example, A0 equals A1 through N, but you can't set it so that without having a random variable in between for AI to be written into AI plus 1. So you couldn't just copy every element along in an array, because at that point you do have an unbounded number of for loops that you would need to nest within each other. But for that, with that one restriction, you're able to have all of the compiled work done, and still be able to cope with the fact that the length of the arrays and such like is not known until runtime.
Great, thank you. I'm looking forward to looking at your work in some more detail. Do we have
Cool.
any more
If
questions?
you do have any.
Oh yeah, Gunesh has a question too.
Hi, so this is all based on JVM, right? I was wondering if you compare your system to other JVM-based probabilistic programming systems, for example, Anglican, Enclosure, yeah.
In what sense? We haven't.
I mean, of course, I think
ones.
I mean it in a runtime sense, or like maybe like the types of models that can be implemented, and like yeah, mainly like from a runtime point of view, yeah.
So we haven't compared performance with other JVM-based languages at the moment. It's one of the, because this is still very much a work in progress. It feels a bit premature, because some places we're very fast compared to other things, and in other places where we've got optimizations that are still on the to-do list, you can end up with quite poor performance, and then go in and do a few simple optimizations by hand, which are things that the compiler should do and will do ultimately, and get 2 orders of magnitude performance increase. And so it feels that we'd be premature to do a comparison based on speed. The main goal, though, was about trying to make it easier for the people that we're running into in product groups to use probabilistic programming languages, because we've been a fan of them for quite a long time with things like the Argo work, but we kept running into people going, we don't want to put that in because it's going to confuse the hell out of everyone.
All right. Okay. Thank you.
Okay, let's thank Daniel one more time. And then we have our coffee break now. In case you brought a poster, this will be a great moment to put it up, and then we can already talk about the poster during the break, and then later on
Oh, wait, no, I better mirror this. Okay, cool. So hello, I'm Tim. I'm from the University of Cambridge. I'm part of the Turing.jl team. And we're going to be talking to you about work we've been doing in extending the functionality of Turing, which is a popular probabilistic programming language written in Julia, to extend it to be able to perform efficient inference on state space models. And so the main goal of this work was to try to provide a flexible, but I guess primarily an intuitive interface for state-of-the-art SSM inference algorithms, while also targeting near optimal, like theoretically optimal throughput.
And I'm Charles. I'm from the Federal Reserve Board of Governors, and so I have to have a quick disclosure here. The beliefs presented by the authors are not a reflection of the Federal Reserve Board or the greater Federal Reserve System. Now that that's out of the way, let's talk state-space models.
Cool. Okay, so what is a state space model? So they're composed of two components. The first is some unobserved latent Markov chain, which is denoted X here. And we receive noisy measurements that we do observe, Y, and these only depend on the current state of the Markov chain. And so this entire model is governed by these three distributions, and these each can depend on the current time step, as well as some hyperparameters theta, which may be known or unknown. And so because of this structure, the joint density of all these x's and y's can be factorized into this neat little form. And this allows us to perform inference in a more efficient way than if we just had a general Bayesian model.
Yeah, so the sequential nature of the state space model yields this relatively intuitive expression of the posterior distribution with a class of algorithms called filters that can essentially be broken down iteratively into two steps, the prediction and the update. The prediction essentially takes the previous values of the previous distribution of states and propagates them forward either by the state space model or some abstract proposal, and the update step, which evaluates its correction and like how accurately it represents the observed value at time t, which, since this is an online algorithm, it's actually quite a bit more efficient than something like MCMC. Online, by the way, just essentially means it has a constant computational complexity at every time step of the state space model. And so this isn't something that you can kind of do like out of the box in like Stan or like Turing. And so this is essentially why we wanted to define this like module. And so in a fully modular setting, since the output of both the proposal and the update step are the proposal distribution as well as the filtered states or the filtered density, we want to work with distributional objects, something that we can take a sample from and evaluate its log likelihood, which makes it not only easier to encourage users to create their own callbacks at every iteration of the algorithm, but it also allows us to make more complicated inference algorithms, something akin to like marginalized filters or array-blackholized particle filter.
Yeah, so I guess as a case study of the flexibility that our interface provides, I want to talk a bit about this special class of Rao-Blackwellizable state space models. So these have a special form where those hidden latent dynamics can be decomposed into two subsets, X and Z, where once we've conditioned on the X, we have some given values of X. The remainder of the model, so the remainder of the latent state Z and the observations, those combine form a conditional submodel that has a special form that admits closed form analytic inference. So a common example of this that frequently comes up in tracking literature would be a model where you have various nonlinear dynamics on the outside, but then after conditioning on those, your position and velocity, as well as the measurements that you receive, have a linear Gaussian form, and so can be inferred using a closed form Kalman filter. So to perform inference on this entire model, the usual technique is using what's called a Rao-Blackwise particle filter. And the idea behind this is you take your usual particle filter and replace the single value of z that you would have in each particle with an entire distribution of z associated with the x in that particle. And so this, in a sense, marginalizes out all the variability in that z, reducing the effective dimension of our problem and therefore reducing the variance of any estimates we would derive from inference. So this is a very powerful technique and can be applied in many settings, and yet we were quite surprised to find that there wasn't a general purpose implementation of this outside of like very specific hard-coded ones for certain research papers until now. And so because of this, I guess, distributional focus of our interface, it's actually very easy to define a general purpose Rao-Blackwise particle filter that can take any arbitrary submodel and any arbitrary closed form inference algorithm. And the way this works is that if we have our empirical particle distribution, which is going to contain many of these pink particles, each with a singular value for an x, an entire distribution for the z, a marginalized distribution. If we want to update this entire particle distribution, what we can do is simply pull out that marginalized state and dispatch to whatever inference algorithm, closed form inference algorithm, is appropriate for that type of marginalized state. So we can then take that updated or predicted state and put that back into the particle distribution. And when it comes to updating, because these distributions are proper sampleable objects, when we do that update step, we can obtain an incremental log likelihood that can be fed back into the general Rao-Blackwise particle filter algorithm, and that's used to update our log weights in the particle container. And so essentially what we've done here is completely decoupled the implementation details of that inner closed form inference algorithm from the general Rao-Blackwise particle filter. And the key thing worth noting here is that this process of doing these closed form updates on every single marginalized state over the various particles essentially boils down to performing linear algebraic operations on very large batches of typically quite small matrices. And so we've taken a lot of care to make sure that we've optimized that sort of operation as much as possible. So we have some benchmarks. And starting from just a vanilla CPU implementation, because we're working in Julia, it's very easy to leverage the powerful multiple dispatch system that it has to use specialized operations that can speed things up. So for example, we could replace all of the base Julia matrices and vectors with static arrays from the staticarrays.jl package. And what this does is it performs very efficient linear algebra by stack allocating small arrays rather than the default heap allocation. And so by just changing like 5 lines of code in our model definition, we can get a 5 times speed up essentially for free. We also have GPU implementations of these algorithms. We have the base default one using cuBLAS, which is the linear algebra framework that comes with NVIDIA's CUDA. We've also, so this framework isn't particularly specialized for this case of large batches of very small matrices. So we've actually written our own custom CUDA kernels, which are like right at the theoretical limits of what you can achieve with a GPU. And so overall, it's many orders of magnitude faster than the CPU. And there's no direct comparison we can make to another package because this is the first implementation. The closest thing would be a PyTorch package called torch-Kalman filter, KF. And so this performs batched Kalman filters, which is, so that operation is a strict subset of the operations that take place when doing a Rao-Blackmores particle filter with a linear Gaussian submodel. And so even though it's doing less operations than the entire thing, our model is still more performant.
So the entire point of this module is essentially solving a single problem. It's getting the filtered states, or the filtered density, the posterior of the state space model. And so for analysis, we essentially designed a system of callbacks that the user is encouraged to implement by using like these distributional objects as like inputs to some callback. And so like for analysis, that's pretty much up to the user to define those. But we do include some of our own callbacks, such as efficient storage of like particle trajectories over time, which is a very cheap way of getting like a smooth distribution without doing a backwards pass of a filter or a sampling algorithm. Furthermore, we've designed a system of modular like resampling, where we not only designed our own very boilerplate resampling algorithms such as the stratified resampler, multinomial resampler, but we encourage the user to then define their own like algorithms. Something a little more complicated, such as like a Metropolis resampler that can be parallelized over like a system of GPUs. Furthermore, something more interesting, or at least something that I find quite interesting, like a differentiable particle filter with use of like entropy regularized optimal transport. I've cited both of these papers, by the way, at the very end. But since we have like a very modular resampling system, we encourage users to do something like this. And it's very easy to do in general. And since I was talking about differentiable particle filters, I'd like to talk a little bit about automatic differentiation within this interface. It's actually quite a bit difficult to do because of the recursive nature of sequential Monte Carlo. But currently, we do support forward mode automatic differentiation using forward diff.jl. And so some motivations as to why it would be useful for particle filters or Kalman filters in general. The low-hanging fruit here is maximum likelihood estimation. That's unfortunately everywhere in fields like macroeconomics and whatnot, stuff that I'm used to. But also, it adds a composability within Turing models. If we support some kind of automatic differentiation, we could then compose a filter within a Hamiltonian Monte Carlo. Furthermore, we could design our own filters like variational sequential Monte Carlo or other algorithms kind of akin to that.
Cool. So yeah, so one other quick point that I'll brush over, and we can talk about more in the post session if anyone's interested, is that we have an extension to this framework which supports multiple target tracking with all the standard data association methods you would expect. And so we're soon going to be adding the ability to add and remove tracks that you were tracking. And at that point, it will have feature parity with StoneSoup, which is probably the most popular framework for multi-target tracking, except we would have the added bonuses of performance and a bit more of an elegant interface.
And lastly, just to present a little bit of that integration with Turing, since we mentioned it in the very beginning, we have a quick introduction to particle marginal metropolis Hastings with advanced MH. It's a very, very easy addition. Essentially design your density function by calling that generalized filters.filter on the toy model. That toy model is a user-defined function that generates a state space given theta parameters, where we set the algorithm to be any kind of filtering algorithm, like a Kalman filter, particle filter, Rao-Blackmores particle filter, and the data is self-explanatory. And yeah, we also have a working version of particle Gibbs as well, as some like MLE, but yeah, it's pretty composable stuff. It's very flexible, and it's very modular, and we're pretty proud of it. So yeah, I think that's it, right?
So we've got the references here. If you have any questions, please ask now, or we can chat in the post session.
Questions? Yeah, okay.
Thanks for the talk. In terms of integration with Turing, have you thought about how users who write their sort of state space model in the Turing probabilistic programming language can hook into this and specify that they want certain parts of the state to be represented with these specialized representations?
Go for it. Yeah, so this is actually quite a difficult problem due to how Turing is architected. In a sense, yeah, it is not like you run through the entire model and can go, this is a state space model, I should dispatch this faster method. Yeah, you're kind of running through the model on the fly. So I think the way we see it being used is probably as a nested model inside of Turing. So in that last example, for example, where we're using it inside of particle modeling Metropolis Hastings, or within the Gibbs sampling abilities that Turing has. But in terms of like, yeah, just writing your model in Turing style DSL, probably not going to happen.
Yeah, it's like kind of tough to infer the latent dynamics from a Turing model. Like there are a bunch of examples like, online where, it's essentially just traversing like a series of function calls, since, it's not like a graphical like probabilistic programming language. There's really no easy way to do that.
Thank you.
Any other questions? Okay, Matthias.
I was wondering to what extent the algorithm that you're presenting is new, and whether the correctness of that algorithm is obvious or needs to be proven carefully. So I guess the question is your contribution the careful implementation and making this actually usable, or is there actually a new algorithmic technique here?
Yeah, no, so these are standard algorithms that, yeah, you'll find them dotted around the place in literature, but it tends to be like, yeah, we've done our own hacky implementation for this one paper and, not done a general purpose one. So yeah, what we're offering is a very general purpose implementation that can be used in wider settings, but also a very performant implementation of it. Like we're really kind of focused on like, getting to that theoretical optimum of throughput. So that's probably the main contribution that we have.
And if I, as a lay person to SMC, want to learn about the correctness of this sort of technique, where should I look? Should I look at any of these sources?
Yeah, so I think, I forget the name of the textbook.
An Introduction to Sequential Monte Carlo by Nicolas Chopin. Definitely highly recommend that one. Yeah. There are a bunch of others, but that's my favorite. Just for general like time series and stuff like that. Durbin and Koopman also have a very good book. Yeah, I don't know. Any others?
Yeah, I can't remember the names now, but I can perhaps check you after.
Yeah.
Thank you.
All right. Any questions? Okay, I had one question, but maybe I'm too unfamiliar with the Turing ecosystem. So how does this plug into Turing? Like, or does it make sense to even ask this question? Like, what's the API and how do they work together?
Yeah. So this is a bit of a confusing point that we've maybe glossed over a bit, in that I guess this kind of maybe sits next to Turing a bit, in that, so the way you would define a state space model with this is kind of independent to the normal Turing app model that you would be doing. You're defining those three distributions: the initialize, the transition, and the observation. So it's more like, yeah, it lives as part of the general Turing ecosystem. We've made sure that it integrates as a higher level as like a nested model, that if I want to take one of these models and use it within Turing in Gibbs sampling of particle Gibbs, or within Metropolis Hastings, maybe HMC once we have differentiable methods working, then yeah, that's kind of the connection between those, but it's not direct.
All right. Okay. Thank you.
Yeah, I'd kind of like to relate this to something like using like a PDE within Turing, right? You're not actually designing that, partial differential equation in the Turing like model itself. Like, there's nothing in Turing that allows you to do that, and so you have to use something like ODE problems or whatever to define that, and then like compose that within Turing. And so that's essentially what we're proposing and what we're doing.
Okay, thank you very much. So if there are no questions, we can thank Tim and Charles one more time. And yeah, so now is the time for the post-hour session. Officially, this is running until 5:30. So I would like to